Welcome to the hardware development workshop. We're very flexible today. I have set alarms, we are fixed for coffee breaks, and we will stop wherever we are when we get to the point at which it's time for a coffee break. We're going to go through quite a few things today, and what I would like to do is do it slowly enough that everyone is happy with everything that we've done. So at the point at which you're sitting there thinking, what on earth am I on about? Stop me and say, what are you talking about? And we will do it as many times as you want to until everyone is happy with what we're talking about. Okie dokie. Go on. Okay, so we have 2 days. We're going to start off with an introduction, and we're going to start right at the very, very beginning with lots of basic principles of NMR. This will perhaps be patronizing and boring to some of you, but I want to make sure that everyone fully understands all of the bits that rely on later. Then we're going to do a long session on how we make and design magnets. That's our biggest session. A slightly shorter session on coils, and then another long one on electronics. And that's what we're going to do today. I don't know when they will start. I don't know when they will finish. It depends on how long it takes us to get through what's on there. Then tomorrow, we'll have a look at the pulse sequences that we use, how you set parameters for the pulse sequences. We'll have a look at how we do the testing of the probes and what it is that you need to do in the process that we follow to do the probes. And then in the afternoon, we've got the practical session where everyone will have a go at building their own. Before we start anything, there are a million different ways that you can approach this problem. This is how we do it. It doesn't make it the right way. It definitely doesn't make it the wrong way, and it mostly works. I'm going to show you how we do it because it's quite streamlined. Everything is free software, and it's all nice and straightforward and easy. There are ways you can do it which are more complicated and cost more money and will give you perhaps a slightly better end result, but our goal is being as cheap as possible to give everyone something which they can use. This may or may not be a good idea, I don't know. So there are 2 sets of online software which I would like to try and use. It may be a disaster, in which case we will completely abandon it. The first is a thing called VBox, which is like an online quiz thing. And so you go on the website and then it shows you the questions and you can tick an answer, and then we all get to see. It's like a voting thing. We use it with our students and it works quite well. It's also very good when everyone is sat too embarrassed to say they don't understand it, and then everyone answers it wrong, and I know that you don't understand it. The other thing is an online post-it board. I obviously up here don't have facility to check the online post-it board. I have not told Nick that his job was to stay online and check the online post-it board, but his angry face suggests he knows now. And that again is just a little place that you can stick post-its. You can say you hate this and you desperately want to go home now. You can say that you like this, you don't like that, and things that you want to get out of it. So I'll show you that as well in a second. Then we'll have a quick look at the people in here who know enough about this that they can help you when you're stuck doing the practice stuff later. And then we'll start with the fundamentals. Very good. Okay, so for magnet design, we're also going to use another piece of software which is called FEM, Finite Element Method Magnetics. And I'll get you at some point to download and install that. It's a small file, it's not very big, but then we can go through and you can actually do some magnet design here and now whilst we can show you how to do it. VBox is the VBox link, but hopefully there'll be a QR code in a second, and then there's the online post-it board. If you scan this QR code, I believe it should take you to one website where you can click the links to get through to all of the other software. VBox is the one that we need first, and then we can have a go with the others. So I'll give you a minute to see whether or not you can get online and see whether or not this works. It's very difficult for me to test it because I have permissions to the site. So if you can go on and just see whether or not you can get on there. In fact, I may do the same. And just see whether we can get on.
Session ID.
Maybe.
Oh, okay.
That would have been a good thing to put on there. Yeah, 167-737-800. Oh yeah, or you can get it as an app. Yeah. So you can just do it on their website or download it as an app. Good. Yeah. Sorry. Go back. Go on. Yes, we can go back.
Hold on.
Nice. So it should just look like that. There's nothing on there. And when we open the poll, it should come up on there and you should be able to click it. Or it won't, but we'll find out. Okay, so all of the stuff that you need should be on that website. And it should give you the links that you need to different things. So results present, press delete to clear, press enter to start polling. So let's see whether or not that works. Yep, that's it. So if you just put in the session ID up in the top, 167-737-800, hopefully it will go on. 737-800. That's promising. That's it. Yeah, perfect. So now you should be able to vote for your which of your choices, and hopefully it will log you on the
It's not doing that.
on the screen. Vote received. Perfect. Very good. Hi, morning. We've not got anywhere yet, don't worry. Okay, 4 more votes to go. So 4 people are on but not voted. Give you just a minute more and let's just see whether or not this works. You might well hate this and we'll just not do it. That's it. Yep, that's it. Okay, we're getting there.
This mirror is really nice.
Okay, I'm going to close this and we'll crack on. Okay, 50-50 split nearly. So this is Vivox. More people are less enthusiastic, but that's okay. The polls like that should always work like that. Hopefully the next ones will be a little bit quicker, and we'll see how we get. Okay. Before we start, I want to make sure that we are both speaking about the same things when we use the same words. Probes to us means the whole of the thing that you plug in to the console. So the whole of the magnet, coils, everything that sits on the little box on the desk is what we call probes. Not everyone does that. And at the point at which you get to huge magnets, so if you do spectroscopy and things like that, probes are just the little coil that goes in the middle. But we're going to talk about probes as being the whole of the thing. Then there is MR, NMR, and MRI. None of them are any more correct than any of the others, but the community has somewhat decided what they mean. MRI is when you get pictures of stuff. NMR is normally when you get spectra of stuff, and MR is when you don't get a picture or spectra. People do not use them necessarily correctly like that because they're not fixed, right? They're all pretty much the same. NMR and MR are the same. MRI needs an image. Okay. These people can help if you are stuck. Not so much now. I will help if you are stuck now. When we start to do practical things and when you start to do the simulations, these people all know how to use it and will be able to help you relatively effectively, or at least know that you're really stuck and then I can help. But grab them if you need stuff. They sort of know what they're doing. Okay, so before we do anything else, it's nice to have a bit of an idea about who knows what already about what I'm going to tell you about, to know how much of this we cannot do, and to know how bored you're going to be whilst we're doing it. This is very much a general view. So if you're sitting there and you've done and you've done loads and loads of this before, go for high answers. If not, go for the bottom. Again, please be honest with the responses because it will help me tune what we're doing. Whilst you are doing the voting for that, I'll give you a bit of an overview of how we came into this. So many years ago, we had no money at all, would maybe every year get about £400 that we could buy stuff with, and that's not enough to buy a system. So we started to try and build our own to do it as cheaply as we possibly could. When you are doing it as cheaply as you possibly can, they are not good. You are not going to learn how to build good NMR systems. You are going to learn how to build NMR systems that are okay, and that's fine. If you're spending £200–300 on a system, it's not going to be good, but that's not the goal. So we are trying to make things that you can either put into labs that have no access to NMR, or that you can take to industry where they want dirt cheap prices and just to be able to stick them in things and look at some rough signals. Okay, let's have a look at what this looks like. Okay, good. So hopefully this will be pitched at the right level. As I've said, please stop me at the point at which you want to stop me. Please don't sit there struggling and not being sure what we're talking about. I would much rather do this really slowly. So right at the very, very, very beginning, there is an atom. This is not really what atoms look like, but it helps us with the explanation. So we have some kind of nucleus in the middle, and this has a sad little lonely electron that spins around and it does things that atoms do. This is what they really look like. Just like a guess at where stuff is. And at some point, it's much more likely to be in the orangey bit than in the purple bit. But this is very confusing for us. So we're going to stick with little balls and circles and everything will be much easier, but it's not quite true. So for us, we are interested in the things that are going on inside here. Most of the time, we are going to be looking at protons. So this is one hydrogen atom. Fortunately, hydrogen is in almost everything that we care about for NMR. The reason we can do NMR with protons is because of a useful property of the nucleus and subatomic particles, which is called spin. Spin is a quantum property. I do not like quantum. We are not going to do quantum because it does not help anyone understand how NMR works. You will reach a point if you really get into NMR where you have to do the quantum because you need it for some really advanced stuff. If we could do double quantum filtered NMR on the probes that we made, we would have done it with a load of money. Okay, if you can get a signal out of these, we celebrate. So we're not going to do any quantum past the fact that I am going to use the word spin because it's much easier to say than the classical equivalent of spin. So spin is this quantum property, and we need atoms that have non-zero spin. If your atom has 0 spin, there is no NMR for us. Fortunately for us, loads of things have non-zero spin, and that means that there's lots and lots and lots of different things that we can do NMR on. Everything that we make only works on proton. Protons are hugely abundant. If you pick almost anything in the room, there will be some protons in it, which means that we can do NMR. You can do NMR on other things, but it tends to be at high field. You need really nice magnets. You need really good setups. So we're not going to look at any of that. But you can do carbon, nitrogen, fluorine, phosphorus, all kinds of different things have non-zero spin. We're just going to look at hydrogens. This is our most favorite molecule that has hydrogen in. What is the molecule? Water, very good. So we have the little Mickey Mouse ears are our hydrogen atoms, which means for every water molecule, we have 2 of those, and that gives us plenty of abundance of hydrogen in our system. Again, the probability distribution for a hydrogen atom is this fuzzy mess. This is what it really looks like. This is much easier. And if we take one of the Mickey Mouse ears, we can draw it like this, and it gets even easier still. Spin, our quantum property, gives us 2 classical properties. One is a magnetic moment, one is angular momentum. Everything that we do in NMR uses both of those properties. Okay, so a magnetic moment is literally like a tiny bar magnet. So if you think of each of our hydrogen atoms as being a tiny bar magnet with this weird angular momentum that's always there spinning, we won't go far wrong. We represent that as the stick with a ball on. The ball gives us this angular momentum, and the stick points in the direction of the magnetic moment. And the green ones take a while to draw, so normally use these. It means exactly the same thing. Is everyone happy with this so far? Good. So if you take a beaker of water, inside that beaker of water, there will be loads and loads and loads and loads of these spins, all ready to do NMR. In water, we have these spins, but they are all pointing in completely random directions. So if I take each of those directions and I add them up as vectors, I will come out with an answer 0. This is why you do not stick to fridges. This is why you can get out of the car, because you are not magnetic. At the point at which you line all of those up, you become magnetic, and you will stick to stuff that is metal, which is not what happens. So something else is going to go on when we put this into a magnetic field. At the moment, they're all jiggling around randomly. Thermal motion will cause them to be completely unaligned, and so we end up with this kind of net zero magnetic force from our system. In a minute, I'm going to turn on the magnetic field, and you'll see the blue cone on the right turn into an arrow, and that arrow is the direction of the magnetic field that we're putting our system into. And hopefully when that happens, you will see that these spins line up, and we will end up with a non-zero magnetization because we will have more of them pointing in one direction. They still jiggle. They are always going to jiggle unless they are at absolute 0. If they're at absolute 0, you can't do NMR anyway. So we're stuck with a bit of the jiggling. But this alignment we call polarization, and polarization is the thing that we need to be able to do our NMR experiment. That's not quite true. So obviously, if you do this, now you are extremely magnetic, and all hell will break loose as atoms are ripped from your body all over the place into the MRI scanner. Instead, we have a situation which is much more like this, where you have a few tens of millions of these. One of them will line up in a direction which is useful to you. This is the difficulty with NMR, MRI, and all MR techniques. There is such a tiny quantity of these which will line up into a state which is useful to us. You are working with tiny, tiny signals. You need huge fields to line up any kind of good significant quantity of these, which is why people like to go to higher field. Fortunately, you don't need that many lined up to be able to do stuff. So you can do NMR in the Earth's field. It doesn't need to be very strong, but you terribly suffer with not very much signal strength. Okay, but this is the thing that sort of underpins what's going on in our system. So Next quiz is how much attention you have paid for the last few slides and how well I have explained it. The letters on the left relate to the things on the right. So take a few minutes to read through the things on the right and then pick which of the letters on the left represents the correct answers on the right-hand side. The N down here is nuclear, so nuclear angular momentum and nuclear magnetic moment.
How high the magnetic field you are talking about to line up most of the hydrogen proton?
If you're just going to do it with a magnetic field, like an infinite number of Teslas, there are ways that you can cheat. So there are some experiments where you can use a lower field and you polarize things that are easy to polarize, and you literally get them to knock into hydrogens. They transfer the polarization and then you get loads of polarization. There's something called dynamic nuclear polarization, and that gives you loads of polarization. At 1.5 Tesla, it's something like 0.0002%. It's tiny, tiny, tiny. But yeah, you need big fields to get any kind of serious number.
I'm sure that I understand correctly how to apply this AAA.
So AAA would be protons, zero spin, and nuclear magnetic moments and nuclear angular momentum. Yeah. Okay, not bad, not bad. So ABA is the correct answer because it's ABBA and that's pleasing. And we need protons. They're our most abundant nucleus. We like protons. The trick for NMR is you need the spin to be non-zero. So it's non-zero rather than greater than zero, because it's fine if it's spin up or spin down. Makes no difference to us. It just needs to not be zero. And then the nuclear magnetic moment and nuclear angular momentum are the things that matter. Charge is another quantum property that is irrelevant to NMR. Well, it's irrelevant to MR. It has some relevance to NMR, but it makes no difference for us. And the same number of protons and neutrons has a higher probability of giving you zero spin, because they might cancel out. Okay. So we take all of these spins and you add up their directions. 1 up, 1 down equals 0. 1 left, 1 right equals 0. 2 up equals 2 up. We sum them and we call this bulk magnetization, which is a vector M. M is the thing that we are going to play with. When we talk about tipping things, when we talk about the directions that our spins are pointing in, we are almost always talking about this bulk magnetization M. We do that because trying to deal with every single tiny spin is impossible. Aside from the fact you don't know what each one is doing, it's this M vector that we're going to be looking at and working out what is happening in our system. Okay, I promised physics. Here is some physics. I'm showing you the physics because this helps us a little bit with understanding what's happening in our system. So this is something called a Boltzmann distribution. And all of these things are things that we know. This is just an equation and we stick them in and all is well. What we want to do is have more spins in the high energy state than in the low energy state. And the number that are in the high energy state as a ratio to the low energy state is given by this Boltzmann distribution. It is an exponential. Almost everything in nature is an exponential, as you will know if you've done NMR. But there are some things that we can do to make this population larger. The things that we can do to make the population larger is pick a nucleus that likes to be polarized. Once you've picked your nucleus, you are stuck with this gyromagnetic ratio. So for protons, it's 40-something megahertz per Tesla, which means that you will have this interesting phenomenon, which we're going to look at in a minute, called precession, at a certain frequency based on the field strength. Planck's constant, it's in the name, it's a constant. We cannot change Planck's constant. There is nothing you can do about it. It's just a number. Boltzmann's constant, just a number. Nothing we can do about it, which only leaves temperature. So the only way that you can change polarization is to increase your field strength, which is B0 up here, or to reduce your temperature. Reducing the temperature is okay for some samples, but not for others. So obviously, if we're doing stuff with crystals where the crystal state changes as you change the temperature, it makes it very difficult. If you are trying to do people in an MRI scanner, you're pretty much limited to the temperature of a person whilst they're alive. So the only thing really which we can do to get more polarization is to increase the field strength. If we take those values and stick in some numbers, you will end up, as I was saying just a moment ago, at 1.5 Tesla, it's something like 0.0002% polarization. This is very, very small, but it's big enough that we can do some NMR. The more polarization you have, the better your signal to noise ratio will be. That's pretty much it. Everyone obsesses over having really, really high field. All it really does is improve your signal to noise ratio. It is not linear either, so you are punished for trying to go to higher field by getting less polarization than you have increased the field by. So we prefer to work with whatever field we are given for a magnet that we've got and do our best to improve everything else to get our better signals. The other benefit of having more polarization and therefore more SNR is you need to average less. So if you are after a dead fast experiment where you know that you need to have lots of signal very quickly, it is much easier with higher field. Okay. So we have polarized a sample, we have not done NMR. A difficulty with polarizing things is some things like to be polarized and some things do not like to be polarized. Even more irritatingly, if I double my field strength, it doesn't necessarily double my polarization in a given material, okay? So we have this relationship that M, our magnetization, will increase for an increase in the external field. So this is not B now, this is H, which is very much the same, with a proportionality constant, which is chi M, which is the magnetic susceptibility. And just for a treat, the magnetic susceptibility is also not linear. So you end up with these slightly weird effects. If you're going to go through and sweep and measure what you're getting as your magnetization for different fields, you'll end up with some really weird things going on. Similarly, if you've got really inhomogeneous samples, you end up with some strange things where you change from one magnetic susceptibility to another. So for people, when we image people, air is very difficult to magnetize. Water in muscles and tissue is much easier to polarize, and you end up with these weird artifacts. That means you struggle to image near lungs, struggle to image in the front of the face, and all of these things going on. So these are some values for this magnetic susceptibility, bearing in mind that it's not quite linear either. Air is incredibly difficult to magnetize, which hopefully is not a surprise because there is not much in it. At the other end, iron is extremely easy to magnetize. So for a given amount of field applied to iron, you will end up with this really big field within the iron and big polarization, magnetization, whatever. I'm telling you this not because we ever use this in practice, but just as an important message when you start to get samples which are strange. So if you are looking at systems where you've got things that are very difficult to magnetize and things that are very easy to magnetize, water in big hard crystal structures, these kind of things, stuff starts to get a bit weird and you cannot rely on theory giving you what you're expecting. Sometimes you need to dig a little bit deeper and see what's going on. Okay, is everyone happy with everything that we have done so far? Good. Let's go then and have a look at our magnetic moments, which we've done, and angular momentum. So angular momentum is our other classical property, and it is particularly strange on every front. Okay, so our vector for angular momentum is represented for reasons I don't really understand by the letter L. And L is a true vector, so it has a quantity magnitude, which tells you about how much angular momentum you've got, and a direction, which tells you which direction that is pointing in. Angular momentum, something that's spinning, has a vector that points through the middle of the thing that's spinning, just to keep it interesting. So if it's spinning this way round, you will have a vector that's pointing up through the middle. And if you have it in our nucleus like we do, it will stay completely constant unless you do something to it. Okay, it's not true of spinning tops and things that you might be able to apply angular momentum to, but in our protons, it is completely constant unless you apply an external torque, so a twisting force. If you apply a twisting force, a torque, you will change your angular momentum at a rate that's proportional. So the change in angular momentum is literally equal to the torque that you apply to the system. If you push it twice harder, it will change twice as quick. Torque for things like bike wheels, spinning tops, and all of these other good things in life is something which we call a cross product. So this little X is not quite as simple as a multiplication, it's a cross product. And cross products are good fun, and you can do nice things with vectors, with cross products. But the only thing that we care about is that in order for a cross product to work, things need to be not lined up in the same direction. Okay, so if my force that I'm applying and the direction that I'm applying it in are in the same direction, nothing will change for our angular momentum. Okay, so I need to have a change, this torque applied, not along the axis of the spin. Which is why if you have a spinning top on a table and you poke it on the end, nothing will happen. Okay, if you poke it on the side, then you start to see this change. So if I apply my torque in a different direction to the angular momentum, we will see a change. Nearly ready? So we're going to have a look at how, we're going to have a look at how this works with something which is hopefully slightly more familiar. So a bike wheel is a thing in real life which has angular momentum. It doesn't quite work out the same as it would do if you were having this as a proton, because this will lose its angular momentum over time. Okay, angular momentum. No. Angular momentum of our bike wheel is proportional to the inertia of the bike wheel, which is how easy it is to start it spinning and how much it wants to not be changed and how quickly it is spinning. So if I spin it twice faster, it will end up with twice the angular momentum. We normally do this with a bike wheel, which has nice long handles on and is dead easy to use. But fortunately, we managed to even get a bike wheel, thank you. And that's very exciting for us. I'll hold this one. So we should be able to see our angular momentum in action. We start with it facing downwards. Maybe we should tip it after. Or I'm nervous. This is the bike wheel, slowly spinning. And the angular momentum of the bike wheel, which it doesn't have very much out in a minute, I'll spin it in a moment. The angular momentum of the bike wheel is pointing through its axle. Okay, so at the minute it is pointing down. The torque which we have on Earth is going to be caused by gravity. So at the moment, gravity is acting in the same direction as the angular momentum of the bike wheel. We try and spin it and then tip it so it's facing downwards. Can we spin it? I don't know. Let's find out. That's it. And then see if you can tip it over so that it's facing. Woo! No, that's too exciting. I don't know how we're going to do that. Let's try once more. Try once more and let's see.
Okay.
That's it. Let's try it slowly and see if you can tip it. Nice. Nearly. Yeah, success. There we go. There we go. There we go. We're going to pretend that this is perfectly aligned with gravity, and therefore nothing exciting is happening. This is because the angular momentum the angular momentum and gravity are both in the same direction, so our cross product is doing nothing for us. If we now get our cross product working so that we have our angular momentum in a different plane to our gravity, we will see some things that are exciting, because we will see torque applied by gravity. And therefore we will have a change in the angular momentum. And the change in the angular momentum is going to go in the third direction. So we have gravity downwards, angular momentum through the axle, which is going to cause it to spin this way. So this weird motion is called precession. Precession is proportional to the angular momentum that we've got in our bike wheel and that torque which is being applied. This works nice.
Yeah.
If I apply twice the torque, it will spin twice quicker. We can't apply twice the torque unless we go to a planet with stronger gravity. If we had as faster angular momentum, we would see this precession change too, okay? But this is the motion which we are going to see in NMR, and this is what everything is reliant on when we're going to be doing our experiments. This makes me very nervous. I don't think we should do it again. Thank you. No, I'm all right. Thank you. Yeah. Okay, so this weird motion is precession. Precession is underpinning everything that we are doing, and thank you. Everything that we're doing in NMR is dependent on this motion. Good morning. It's dependent on this motion. We have exactly the same features in NMR as we have with the bike wheel. If things are not 90 degrees to each other, it works badly. You can be a bit off. If you're really off and if things are aligned with each other, nothing good will happen. So that's one of our biggest things that we need to be mindful of when we're trying to work out what's happening in our NMR experiment, is things particularly B0, our static field. Our static field and the force that we're going to apply, this torque that we're going to apply, need to be 90 degrees to each other for that to work most effectively. So the same applies to our spins. And this is Block up in the top right there. And he did some work with various other people to come up with the set of equations which tells us how this happens in our processing nuclei. You'll notice it has many of the same features. It is a cross product of two things, our magnetization vector and our B0, our static magnetic field. And we will get a rate of change in that in our magnetization, which is proportional to the strength of our magnetic field. There is a proportionality constant again, gamma, which is our gyromagnetic ratio. This is fixed for a given nucleus. If you change from proton to carbon, you change the gyromagnetic ratio, you change how quickly things spin with this angular momentum and our precessional motion, and therefore you end up with a different rate of change, a different frequency of your precession. That is a constant. If you double your field, you double the speed of precession. Okay. So for us, we have our fixed precessional frequency based on that magnetic field, gamma times B0, and that is almost there to giving us an NMR signal, but not quite. We need to come back to our magnetic moments. So we have now tiny bike wheels processing around, and along the axle of that bike wheel is like a bar magnet. Remember our stick on a ball, which means you have this weird precessional motion of a load of bar magnets. And if you have magnets moving in a circle inside a coil of wire, you will pick up a voltage. So this is how dynamos used to work, for those that can remember dynamos. Or generators all work like this. You spin a magnet inside a coil and you end up with this sinusoidal voltage coming out the end. We can do exactly the same with our spin system. You get them processing, you stick a copper coil around the outside and you'll get a pretty wiggly voltage come out the end, which is our signal. We call that the NMR signal, because it is the signal from NMR. Ooh. So to do our experiment, we need to have a sample which has non-zero spin in its nuclei. Doesn't matter what, but we're going to use protons. You stick it in a big field or a small field, but some field that's going to polarize the system. We call that field B0. That will give us a non-zero magnetization in the same direction as the B0 which we have applied. If we apply B0 this way, we will have magnetization this way. We, at the moment, have not satisfied the cross product. B0, magnetization, no precession, no signal. So we need to be able to apply that torque to our spins in order to tip the direction that they're in and to get them from aligned with B0 to aligned in a different direction, okay? And then we will get this beautiful precessional motion. I don't think I have it in me to do this. If you take the bike wheel and it is spinning and it is precessing and you poke it in the third dimension, it will tip over. So you have seen me do that already. It's how I managed to tip it into aligned with gravity. That same thing can happen with our nuclei. Obviously, you can't go in and poke them, so we need a different way to do the poking. Fortunately for us, they are tiny magnets, and tiny magnets don't mind being poked by other magnets. And when you poke a magnet with a magnet, it will move. So we're going to do exactly the same thing with our spin system, and we're going to be able to tip the direction of our spins into something which will allow them to precess. Sorry, there's a lot of text on that slide. The poking field, which I may now call it forever, is called B1. So B1 is the force that we need to apply to get our spins to tip into a direction that they will be able to precess at. That needs to be at 90 degrees to be zero because we need to satisfy the cross product. Just like the spins precess around B0, if I apply a field this way, they will also precess around that field just the same. And I can pick any sort of arbitrary direction and the spins will precess around that field. That gives us a new torque. So instead of having just B0 in there, now we have B0 and B1, and they are necessarily pointing in different directions, and it makes stuff weird. If you just have one field this way, precession happens like this. Have one field this way, precession happens like this. If you have one this way and one this way, you end up with these nice patterns of stuff which precesses around with this kind of interesting path. B1 is necessarily small in comparison to B0 for two reasons. Number one, it's very difficult to make fields which allow you to do this optimally, as you'll see in a second. And so it has to be smaller. The second is we're only going to do it long enough to tip them from this plane into this one. And that might be a couple of microseconds if it's a tiny pulse. It's like picoseconds if you've got something big. So we actually don't need it to be big. It's very small, which means that we're not giving the system any more energy. So our system doesn't care that it's had B1 applied and it will just tip over very easily. If I was to do it on the bike wheel, to do it efficiently, I need to follow the bike wheel round as it's precessing, okay? If you think about someone on a swing, if they're swinging backwards and forwards and I want them to get higher, I need to poke the bottom of the swing. There's a lot of poking today, I'm sorry. You need to push them on the back when they're at the top of their swing. You just randomly shove someone whilst they're on a swing, they will fall off. They're not going to get any higher. Worst case scenario is you push them at the wrong point and you end up with a swing in your face. If you want them to get higher and higher and higher, we need to do it at the same frequency as they're naturally swinging at. That's exactly the same for NMR. Right? This is one of the resonance bits. If we do our application of B1 at the same frequency as they're naturally precessing at, then they will tip over nicely. So we need to use our equation from before. We know they're precessing at gamma B0. If we apply B1 at the same frequency as gamma B0, we will tip them really efficiently. That also then means that we can work out which direction they're going in a little bit easier. So I'm going to show you now this tipping. I'm going to apply B1 along the blue axis, B0 is along the red axis. So we've satisfied our cross product. I put my pulse on there and I'm going to leave that pulse on until my spins have taken this trajectory into the XY plane. So this is a 90-degree pulse. We're taking them from aligned with B0, 90 degrees into the XY plane. We traditionally apply B0 along Z, but as long as you define what you've done, it makes no difference, as long as B1 and B0 are 90 degrees to each other. Once I've done that, it will then go back to its precession about B0 and not tip anymore, okay? If now we do the same thing, start. Okay, if now we do the same thing, but I apply twice the amplitude of B1, what's going to happen to the speed of our spin tipping? Bit faster, slower, same. What do you reckon? Faster by 2. Which means, it's gone back to the beginning. Which means that in order to tip our spins into that plane now, there we go, there's our twice larger pulse. In order to tip our spins into that same plane with a twice larger pulse, I need to do it for half the amount of time, because the speed with which we're tipping our spins is proportional to the strength of B1, okay? The thing that matters for how far we tip our spins is the integral of that pulse. So the height of the pulse times the width of the pulse will tell you the angle that you're going to tip your spins at. You can maths this problem, you'll get an answer which in my experience is always wrong, which is why we never do it. Anyone that has used a commercial spectrometer or any of these things, at some point you will have to calibrate that pulse to work out what it actually needs to be. There's a lot of other things going on in the system that make that not perfectly efficient, okay? So the integral under that pulse, the area of the pulse, the height times the width, is going to tell us how far it's going to tip. If I applied the second pulse, so the twice stronger pulse, for the same amount of time, where would my spins end up? Seeing some pointing downwards, so they'll just keep going, okay? So a certain amount of time will give us a 90, twice that amount of time will give us a 180 for the same pulse, okay? Is everyone happy with this? Does anyone have any questions about this? Good. Okay, so now we can do our whole experiment. We start off, we're going to do it to a pair. We're going to stick it into our magnet. And we're hopefully going to be able to get things to do some NMR. So we have B0, which is along the cylinder of that magnet. And that's going to give us a magnetization for the spins which are useful to us in the high energy state aligned against that magnetic field. We then need to hit it quite hard with our pulse. And for most field strengths, gamma B0 will give you something which is in the megahertz range. So this is radio frequency, which is why it's an RF pulse. If you do this in Earth's field, it's low enough that it's an audio frequency pulse, but the most NMR that we do is going to be RF in the megahertz, okay? That needs an amplifier to do that. We're going to apply that to this copper coil, 90 degrees to B0, and it's going to cause our spins to tip. We wait for the amount of time that they need to get into the next plane, and then we turn off the amplifier that's powering these spins with that pulse, and then we're going to listen to what's being induced in that coil. So it's one coil normally, which does the transmitting and the receiving, applies the pulse, and then picks up the signal. If you then measure the signal which you've got in that coil, it will be a sinusoid. And the reason that it is a sinusoid is because you have a thing which is rotating around. So if I look down on the top of the bike wheel whilst it's processing, I'll have a view that looks like this. We're looking at the axle of the bike wheel because it's the direction of our magnets. And so we're going to watch that now rotate around. And as that rotates around, you will see it carves out a sinusoid. If you look at the amount of signal which you've got along X, when you've got maximum X, you have 0 Y. So depending on which direction you're looking in, you will have a sine or a cosine, okay? This is important for NMR, as you'll see when we get to the electronics part, as sometimes we collect both of these. So if I'm only looking along X, I might miss stuff that's happening along Y if all I'm doing is following it round as a sinusoid. So we'll often collect these And for reasons that makes maths easier when you're trying to then get your signals processed in the software, we often have these as real and imaginary components. They're real and imaginary because it's easy to do the maths to work out which direction they're actually pointing in, but that's all it means, okay? So the real and the imaginary component are just things that are sine waves that are in phase with X for real and in phase with Y for imaginary, okay? Okay. Oh, why is the app ID not on there? Maybe this will work. Let's see whether or not this is still connected to the same session. Yeah, nice. Okay, so what do we do to get our NMR signal? Need to read these slightly carefully. They're not a trick, but you need to check that the things are in the right order as well as checking that the things are the correct things. Okay. Last few seconds, last couple of responses. So the short pulse is just the right amount of time to tip it by 90 degrees, not to give away the answer. We typically see for benchtop stuff, the 90-degree pulse is normally in microseconds. Big stuff, so MRI scan of the 90 is 7 or 8 milliseconds. The frequency that you're operating at doesn't make a great deal of difference, but the size of thing you're trying to apply it to makes a really big difference. So if we've got a tiny coil, you don't need very much power, which means I can have really short pulses. The same amount of power on that I apply to that tiny RF coil on the MRI scanner will lead to RF pulses that are measured in minutes, which doesn't work. So we can up it to a certain point, but it needs to be big enough.
Value is like around.
So we use, so for something like 25 watts, it would be 5-ish microseconds, 10 microseconds, something like that. But it depends very much on the size of the coil. Okie dokie. Not bad, not bad. Phew. So top one is correct. We put our sample into a big magnetic field, it gets polarized. We apply a short pulse of RF and it will tip our spins from aligned with that field to 90 degrees. And then we collect the signal that comes out, and that is the free induction decay signal that you see on lots of the spectrometers. The second one does not give you an NMR experiment because you need to have the polarization for our RF pulse to have any effect. And the last one is interesting. So the last one is not really a basic NMR experiment, but will give you NMR. So actually that's a thing called continuous wave NMR, which is really good fun, and is what we had before we went to pulse NMR. It's quite difficult. So we abandoned it and went to pulse NMR. People are picking it back up as a thing now because we've got better electronics and you can actually do it at some size. But the top one is the answer that we're looking for our simple NMR. Okay. This is how NMR works. We will do a bit more of this later, but this is our kind of entry-level NMR experiment. We can do a pulse, we can get a signal, and we're quite pleased with ourselves. We want to do this now on something which is cheap and which we can make. So there are a couple of things that we now need to translate from that information, which we now know, into physical things that we can build. The only things that we need, other than things that can make the pulses, is a magnet and a way to transmit the RF into the sample. That is it. That forms the NMR probe. How good each of those things is will determine how good your signal is, but that is all there is that you need. There's some examples of ones that we've made over here on the right-hand side. They can look like anything. If you have a magnet and an RF coil, you theoretically can do NMR. It's a little bit more to it, but those are the only things you really need. The better they are, the better your signal will be. So we're going to have a look in the next session at what we do to make them. And we'll start off with the magnet simulations, which you can see on the right-hand side, and how you match the coils to achieve that. We are going to do this with permanent magnets, which are made of a material called neodymium iron boron. They're very magnetic, very cheap, and they come in whatever size you like. Okay. When we do the magnets bit, we'll get you all to sign a risk assessment. That's a problem for tomorrow. Which Nick's going to write down so we remember. Magnets are really good fun, but they're very strange, and they will stick to stuff. They'll stick to you, they'll stick to other magnets, they will stick to bits of desk. And that's the thing that makes the magnet building quite good fun. But those are the sorts of things that we use for the magnets. Coils are literally a bit of wire that's wrapped around a thing. Oh, look, there's a coil. Congrats. That's it, right? We will see in the session after next how you do that to be effective. If you have a piece of wire, you have the potential for it to be a coil, okay? And then finally, we're going to have a look at how you test them. Tomorrow you will make some and you will test some, and they will work. But that's pretty much it that we're going to look at for the fundamental principles. So what we're going to do now is we're going to use this next bit of time to make sure that everyone can install the software that we need for the next session. We're very close to coffee, so there's no point in starting. Okay, so we'll just, I'm going to show you the slide that we need for magnets. So the page that we had open earlier should work on there. Ah, lovely. So you can scan this one and it will take you to the link for FEM. You can Google FEM with 2 M's and it will almost certainly find the software. It's not very big. It's not that powerful, but it is extremely free. So I'll give you a couple of minutes to see if you can download it. I don't know whether or not there is a version for Mac. Yeah, so that will work on the laptop. Do we have a Mac version?
I thought it was.
Let's see. Let's see whether or not we have a Mac equivalent.
We need to get into details about the README file on the.
No, as long as it's installed, I will be README. Okay, so we will have a go with FEM in a little while. We'll try whilst we have coffee to see if we can do something that's similar on a Mac. And we'll go from there. We'll start off and we'll do some more lecture-y stuff. We'll go through, I'll show you the principles of building magnets, because there's quite a lot to magnets. Again, we will start with a little bit of physics, because then it makes me qualified. And we'll go through and look at what magnetic materials are, how they work, and how we can use them to build magnets. Coffee?
Yeah.
Good. Very good.
Half an hour break then.
Yep, perfect. So if it's 2:15, that's 1:45 to come back. So 10:45.
Ben şimdi yeni önemli bir kez görüyorum.
What time are we doing lunch? What time are we meant to be finished for lunch?
Go even before 12. It shouldn't be late. It can be earlier.
Okay.
Anytime you want.
Yeah.
Güncelledi. Şeyden yapmaya çalıştım. Deneyeceğiz.
Okay, are we ready-ish to start? I've added some more instructions onto the website with the software on.
Nick.
Sorry. So there, so there, did you back? There should now be some more instructions on the website with the software on for Macs. Don't know if it will work, but there is now instructions. I don't know if we'll quite get as far as that before lunch, so we can have a play over lunch as well and make sure that's working. Nice. Okay, so we have done the introduction. Now we're going to do magnet simulation. And the starting point for magnet simulation is to have a look at what magnets are and how magnets arise. The reason I want to do that is to just make sure that when we're talking about magnets, we're all talking about the same things and that you understand a bit more where it comes from and why it works like it does. I think there is AVVox in there again. I don't know why there's no ID on there, and that probably means I've not joined a session. Is there? I don't know how to get rid of it. Let's play it and see if it will go away. Go away. We might just be stuck with it. I don't even know what it's from.
Dr. Rob, if you click on the Spotify icon underneath, like the
Oh,
it will go.
Spotify is open.
Yeah.
Well spotted. Yes, success. Thank you. That's good. Let's join this. Started. That's also working. We are good to go. Thank you. Okay, so again, just like the whole view, same process for magnets, please. but now specifically for magnets. So if you have made magnet assemblies before, even if not for NMR, tick. Oh, I can hear myself again. Okay, good, that's working. Right. Good, also pitched at the correct level. Okay. There are three broad types of magnetic material. All of them are magnetic materials. And we define them based on what happens when you stick them in a magnet. Okay. So on the left is a material not in a magnetic field. On the right is a material in a magnetic field. The top one, which we call ferromagnetism, are the magnets that we're used to. So permanent magnets are ferromagnetic. If they are not in a field, they are still magnetic. So this is just the same as our arrows on our sticks and balls. They are just as magnetic in or out of a field. Then we have two other types which are a bit more weird. Paramagnetic things are like what we've already looked at. So they have some amount of magnetism, but it's all in random directions and they are not magnetic. If you put them in a magnetic field, they line up and become magnetic. So that is the one which we've also looked at. And then diamagnetism is the one which is the most strange. It has absolutely nothing about it which is in any way magnetic until you stick it in a field, and then it desperately tries to not be a magnet, and it will oppose the field that you've applied to it. So those are our three types of magnetism. The one that we care about, have a pointer now, the one that we care about to start with is this one, which is ferromagnetic materials, and we'll come back to those a couple of times. There are two types of material within ferromagnetism, and they're the ones that we're going to look at today. And they are hard magnetic materials and soft magnetic materials. Magnets are hard, teddy bears are soft, rocks are hard. These are our two types of magnetic material. And they have different properties which are important to us, but we need both to make really nice magnets. Okay. So if we zoom deep down into the inside of a magnet, we will see microscopically these really weird shapes inside. So this is a very clever type of microscope image that measures magnetic properties. And the different colors tell you about the different directions that the magnetic parts are in. And these stripes or domains are areas where we have lots of things lined up in the same direction. If you have lots of things lined up in the same direction, they will have enough things pointing in that direction to be magnetic. So these are our permanent magnets, have lots of these domains that are lined up in the same direction. When you first try and make, we're not making magnets, but at a factory, if you were to make a magnet, we start off with a material that looks a bit like this, and we have these domains, but they're all pointing in different directions. So at the moment, I think I do. So if we take this stripy one, the light grey perhaps points to the left and the dark grey perhaps points to the right. So on average, that domain at the moment is not magnetic to us, but they are big, they're large areas in there. And if we can somehow align those together, we will end up with a material which is a permanent magnet. So we take this domain, I've put it over here now, and we have these little domains on there and they're all pointing in different directions. If I put that into a magnetic field, just like we polarized ourselves earlier, we can do the same with that magnetic material. So we can do that with a solenoid wrapped around it that we can apply a current to. It will make a field, a magnetic field, and that is going to influence those domains. To start off with, they are all pointing in different directions. when we have no external field. So H again for our electric field that we're applying. As we increase that field, first a little bit, go a little bit. A little bit, the domains start to shift and we move our small domains that are in the same direction will start to grow in favor of the ones that are pointing in the wrong direction. As we increase that, that will happen more and more until we end up at the point where we now have almost as all of our domains pointing in the direction we care about. One of the things that determines what we call the grade of the magnetic material is how well we've done that. So our really high grade magnets will have almost all of the domains pointing in the same direction. Our weaker grades will have more that are pointing against that. But this will now give us, when we take that field away, a really nice magnet. This is a weird property and we play with it a bit in different systems. So when we are taking a magnet, okay, well,
Give it a once.
yeah, close your eyes.
Pointer. No, it's
I've plugged the pointer.
yes.
Now it's the laptop. If we take away the field, we will lose those structures. So the trick with making permanent magnets is we need to do that whilst it's in a state where we can manipulate domains. So for most of the magnets that we are going to make without a PowerPoint. Oh, come on.
Mine was restarted. Right.
Did it?
Yeah.
That's nice. This means there's an update coming, doesn't it?
Yes.
I don't know what it's doing is the answer.
Mm.
Right, I have a mouse pointer again. Here we go. Here we go. Mm. That's still not the slide I clicked on. I don't know is the answer. What it is the PowerPoint being closed and reopened, I think. But even that's doing something slightly strange. Maybe. Okay. Whilst we have our magnet in a state where we can manipulate these domains, we can change the fields and we can change what we're getting from our magnet. To do that, we will normally do it at a reasonably high temperature, and it means that the domains can actually move around. They're not fluid in the sense of being a fluid, but the domains are like a fluid. We then get graphs which look like this. So on the x-axis is our magnetizing force. So this is the field in our solenoid that's moving the domains around. The y-axis is the field of our magnet, okay? So we have these hysteresis plots or BH curves, and they give us some interesting properties that we need to use in our magnets. This is true for hard magnetic materials, this is true for soft magnetic materials, but only for this shape, only for our ferromagnetic materials. So if we start in the very middle of that, it's a fresh magnet, it's manipulatable, but it's just sat. And we apply our magnetizing force in our coil, we will move from the left to the right-hand side of the plot. So we start off, maybe I'll use the pointer on the screen if it's working, it is, and we will start to come up here, okay? So the more the force is applied, the more we move those domains and the more we end up with a magnet. If I leave it being manipulatable and take the field away, it will come back, but it's now going to come back at a point that's higher than 0, and that's the thing which we call remnants. And if we now leave it like that and cool it down, we will have a magnet. You can do the same again in the opposite direction, but it takes a bit of energy to start with to start the domains moving, and how hard you have to force it back to zero is something called coercivity. It doesn't matter so much for the permanent magnets, but it's important for iron when we're going to use that as a soft magnetic material. And you can do that backwards and forwards. And we use this as a way to measure the properties of materials. But the thing that we care about at the minute is remnants. It's kind of fixed by the material. So there is a maximum achievable magnetism that you can have for a given material. And that remnants is very high in the neodymium iron boron magnets, which is why we like them. So we take our magnetic material, we heat it up, we shoot it over to the top, and then we let it cool down with those structures in place, and we end up with a nice magnet. That then gives us proper definitions for the difference between a hard magnetic material and a soft magnetic material. Hard magnetic materials are hard to magnetize, but once they're magnetized, they stay very, very magnetized. The soft magnetic materials don't take much energy to actually start to be magnetized, but they can't stay magnetized as magnets once you put them back into equilibrium. So if you take a piece of iron at room temperature, it will be a magnet. So magnets stick to iron because of this. But once you take the field away, they collapse back down and they cease to be magnetic, unless you do this kind of cycling to build them up. Soft magnetic materials, iron, stuff with iron in, steel. Those are the ones that we care about. Our hard magnetic materials are things like ferrite, which are like the normal bar magnets that you have. Neodymium iron, boron, samarium, cobalt are all of these permanent magnetic materials which we use. Those same graphs look different for paramagnetic and diamagnetic materials, and I'm showing you this for completeness rather than because we're actually going to use them in building of the magnets. But you can see what we had before. Our paramagnetic materials, as you increase the field that they have increases, but when it's taken away, they go back to zero. Diamagnetic do the opposite of that. The only one which is exciting is super paramagnetism. And so you may come across super paramagnetic nanoparticles. We use them quite a lot as a tracer. And if you put them in a very small field, they very quickly become extremely magnetized. And they're quite nice to look at on the MRI. And they're good for kind of doing interesting things as a tracer. Good luck. I was feeling mean when I wrote this, wasn't I? Select as many as are true.
On a plane.
Yes, this will have been on a plane. In fact, this was during the turbulence over the Czech Republic. No, you can select as many as you like. As many as you like. Get more than one answer. Yeah, more than one correct answer.
Mine was a 1.5 to
And we've lost the number.
167. I've got it printed up. 167 737 800.
Okay.
167. Oh, yeah.
That is actually closed.
Oh.
Why is this one the other one?
It's too soon for a quiz. It's always too soon for a quiz. Yeah, it should change it into the X's at the top should really be the idea. I don't know why they're X's. No, they weren't. It was working before the laptop decided it didn't want to. Close that now. Okay, good. They can be magnetized with the presence of an external field. Very good. Ferromagnetic ones can be hard or soft. So our hard ones will stay as permanent magnets. Our soft ones just like to be magnetized. Remnants is how much field is left when you take the field away. So that one is correct. Coercivity is the very mean trick one. That's how hard it is to magnetize it rather than how much field is left. And the last one was obviously because I was not having a very good time. So the limit is set by this saturation. So that very top point on the graph is fixed for a given magnetic material. So there is only so magnetized you can make a magnet. And we'll look at that a bit later with the grades of neodymium which we can get access to. Okay. So there are 3 correct answers. 1, 2, 3, 4, and 5 are not quite true.
So what is the ionization? 167, 767, 737, 800. 7.
What's the first number?
167.
167, 737, 800.
And the fourth one is not correct.
So the fourth one's not correct. The fourth one is very mean. So the fourth one is remnants, and coercivity, which doesn't appear on there, is the initial push that you have to give it to magnetize it. Yep. Okay. Unlike the things which we've looked at so far, everybody agrees on these things which we're now going to see. If you take a magnet, you can draw on the magnet the field lines which tell us some interesting things about the properties of that magnet. They don't always look like they have as much information in as they do, but actually there is so much information encoded in the black lines on there. And it takes a little while to pick apart what they are. The first is the field lines should always go from the north of a magnet to the south of a magnet. Okay, so you'll see if you look at the top, all of the arrows are pointing out, and at the bottom, they're pointing into the magnet. This makes sense because it's sort of how compasses work. So if you take it, it's going to point along to the direction of north. Okay, so they come out of north and go into south. They must start and end in a magnet. This says the magnet, but if you stick another magnet with it, they can go from one to the other. Okay, but they must start and end in a magnet. There are field lines on this picture which do not go from the magnet to the magnet. They just disappear into space. That is not because they are violating the rule of must start and end in the magnet, but it's because it's inferring that that's what they do. So actually those lines are just too big to fit on the PowerPoint, so they're not there. When you see the lines like that, they're still joining round in the same shape. They are still there, which means that on a magnet like this, I think this is probably going to push this far too far, but we'll see. It is pushing it far too, nice. So actually these lines are doing this and you can't see them. And now you couldn't see them because they would just take up too much space, but they are always there and there will be as many coming out as are going in, so you know which ones connect to which other ones. The more lines there are, the stronger the field is. And this one is very important for us. If you take a given circle like this and you count the number of lines in it, you can approximate how strong the magnet is at that point. So this magnet is very strong at the top. There's lots of lines in the circle, and it's quite weak down the sides because there's not very many lines. That means if I take another magnet and I bring it near the top of that, it's going to feel a really strong pull. If I take another magnet and put it near the side of that, the pull that it feels will be much less. Okay, so the more lines there are in our given circle, the stronger the field is. The stronger the field is, the more things are going to be pulled into it. So you will sometimes hear our different materials described by how strong they will attract other things. So ferromagnetism has a very strong force on other things. Paramagnetism has a weak pull on other things, and diamagnetism has a weak opposing force. Okay. When we talk about magnets, we normally work in a unit of Tesla. So Tesla makes a lot of sense for magnets because most magnets are measured in an amount of Tesla. If you take an average bar magnet, it will be some hundreds of millitesla, so 0.1, 0.2, 0.3. If you take something like a neodymium magnet on the surface, you might be 0.5, 0.6 Tesla. If you take something like the MRI scanners, they're normally 1.5 or 3 Tesla, but it gives you a bit of a feel for those kind of sizes of magnets. The definition is very stupid, but it makes sense. I will share with you the definition for completeness, but it doesn't really matter when you're building magnets. But the definition is if you have a charged particle with a charge of 1 coulomb and you put it past a magnet of 1 Tesla, it will feel the force of 1 Newton. So that charged particle feels like it is carrying an apple in the direction towards us. This was quite a difficult picture to draw. So if the charged particle is traveling this way, the field is this way, just like with the bike wheel and all other things in physics, it's a cross product. So it feels the direction of the force out of the power point. Out of the power point. Away from the magnet. So the distance is the distance you need to feel a strength of 1 Tesla. So if you were to take a 1/2 Tesla magnet and pass it there, it would be 1/2 an apple. This does nothing for us, right? It means nothing. We don't have charged particles that are 1 coulomb exactly that we're playing with. We don't have apples. They're very small. Apples are big. What's more useful for us is a feeling for how strong magnets are in something they call pull force. Pull force is not defined. Everyone argues over how it should be defined, but the gut feeling for it is if you take a magnet and you stick it to a big thick iron plate, how heavy a thing can you hang on it before it falls off? So a 10 by 10 centimeter by 10 centimeter cube of neodymium on a big thick steel plate can hang 150 kilograms. Okay, they are strong. We will do this many, many times between now and you touching the magnets. If you take 2 magnets, yours are not this big or this strong. If you take 2 magnets of this size and you put something between them like a finger, that's 300 kilograms of pull force, which is not very nice. Ours are much weaker, ours are much smaller, but just as a feeling for that kind of force that we're getting on our magnets. You will sometimes see the unit of Gauss. It's hung around as well because we use Gauss meters and we use them to measure Teslas. Gauss is a stupid unit. It's 10,000 Gauss to 1 Tesla. And you literally just multiply them up to get the answer. Okay. Everyone happy with this so far?
Yes, before we ask too much, I want to ask you, normally we are pointing the magnets to decide north and south for all of magnets, but I don't know how we decide on pole.
Okay. You mean when we measure them? Or do you mean?
In the lower thing?
Yep.
Okay, you are pointing, you are drawing a line on.
Ah, okay. The line on the magnet follows the rules. So the line, its field line, will go from north to south, which means inside the magnet, we would draw the arrow that way. So the arrow on the magnet goes from south to north, so that its field line goes from north to south.
How do you know the north and the north part?
The Gauss meter, so you will use our Gauss meters tomorrow, and on the back of the Gauss meter, it tells you which way up the probe needs to be that north is positive. So the button, if you've got the magnet and the button is facing up and your reading is positive, the arrow is going up. You can do it with a compass. So if you take a magnet and you put a compass over the top of it, the compass will point along the field line. So the compass is pointing in the direction that you draw the arrow. which is good if you don't have a Gauss meter. Good luck doing NMR, but it's good if you don't have a Gauss meter. Good question. Okie dokie. Next quiz. Less mean, but still very mean.
Where we can't no longer measure with our instrument is where we develop elements.
Yes. So Nick has raised an interesting point, which physics is a bit rubbish, which is where a magnet ceases to be a magnet away from a magnet. If you take the true definition, a magnet back in Nottingham is technically still a magnet here, because the field lines go infinitesimally out. Obviously, that's stupid. We would consider a magnet to be over at the point at which you can no longer measure it. But we also have extremely sensitive measuring kit, like is required to put them on an aeroplane. So they differ. So that's interesting. So the shipping definition. So if you wish to take magnets on an aeroplane, you have to package them such that 4 meters away, a compass is deflected by less than 2 degrees, which is sensible because you don't wish to crash the plane. That is not actually that easy to achieve, right? It sounds dead easy, but for a magnet like the 150 kilogram pull force in a suitcase, you will measure 4 meters away as a little bit of a deflection. And that's something which is important to bear in mind. So if you just take a big magnet and you're like, oh, this looks good, and we'll do NMR on it, it will upset many things in its vicinity and you will get stuff stuck to it. So they do go a fair old distance. Anyway, I digress. Let's see how we have done. Nice. So arrows point from the north up and around to the south. There isn't really an easy way to remember it other than sticking a compass next to a magnet and drawing the lines in the direction that the magnet is going, but then you still don't know which one to have as north and which one to have as south. You just have to sort of remember. They must start on the surface of a magnet and end on the surface of a magnet or a magnetic material. So if you stick a piece of iron next to that, you could go from the magnet to the iron and then from the iron to the magnet. Okay, but they must start and end on something, which is magnetic. The number 4, I think, was mean. I meant it to be the opposite of number 3. But actually, you can draw them anywhere in free space as long as they start and stop at a magnet. So that one was me being stupid. 100% on 5, which is excellent because we're going to use that a lot in the next few slides. And I haven't decided on whether or not I think 6 is sort of also true, because we've not talked about why it's not true. So 6 is not true because you don't know if those magnets are pointing in different directions. So you could have 10 field lines all parallel, very homogeneous. You could have 5 this way and 5 that way. There's still 10, but now your magnet is extremely inhomogeneous. Okay, so that's probably perhaps a point which we should have added on here. The homogeneity of the magnet is such that if you take 2 squares next to each other, the field lines are in the same direction and there's the same number of field lines. Okay. So To achieve NMR, we want three-ish things. We are talking now about doing things conventionally and building systems which just work. There are systems available which do not abide by these rules, but we're not going to talk about them at the moment. Okay, we might touch on one a bit later, which is the typically large areas in the same direction. The trick is the more strong your field is, the more polarization you get, the better your SNR. The more homogeneous your field is, the more of your sample will be at the frequency which you're trying to work at, and therefore the better your signal to noise ratio will be. And typically, if things all point in the same direction, it will be easiest to get this 90-degree requirement for B1 and B0, and therefore you will have better SNR. The exception to that is a magnet which they make in New Brunswick, where you have the magnetic field, which is a weird shape, and then they make an RF coil, which is a weird shape, so that you end up with the weird shaped edges to capture more of the field. And the surface GAR field, which is gradients at right angles to fields, where it's even more weird, and the RF coil is completely designed to match the surface field on the magnet, but they're both what I would term unusual setups. Okay, so how do we do it? We want the strongest field to get the best signal to noise ratio. So the answer is that you go to a field which is stronger. Stronger. The more this way you go, the better it is for your signal to noise ratio. And we do that pretty much by changing the type of magnet that we're using. So neodymium magnets come in quite a few different grades, and they are numbered thus with an N, which is the normal grade of neodymium. You get a high temperature one as well. But the N is the standard grade of neodymium, and the bigger the number is, the stronger the field is at the surface of the magnet. The bigger the number, the more the money. Okay, so if you're trying to build cheap magnets, we will often be down N38s, N42s. If you have lots of money, you can spend it and get the highest grade of neodymium, and you will end up with a bigger field. The flip side of that is the bigger the field, the harder the magnets are to handle. N52s are spicy magnets. They are not fun to deal with. They will stick to everything, and as you get them big, they become very hard to handle. We have for tomorrow N42, which is not that much different, but it makes a surprising difference when you're actually using them. So again, this is about matching the amount of money which you have to spend with the strength of the magnet. There is a different way that you can do it. So you've picked a magnet, and we can do other things to increase the strength of the field. So if we go back to the principles of the field lines, if I could come up with a way to squeeze those field lines closer together, I will have a stronger magnet. And this is why the field lines are a nice way to look at it, because you can see intuitively what you need to do. That's not how to do it, but what you need to do to get the magnet that you want. So if we're looking down at the top of the magnet, I want them to be as upright as possible and to get as many of them in. If I squeeze them in at the side, they will naturally become more upright to give us our field around, and there will be more of them on the top. So I need a way to poke it on the side like this. Fortunately, we know there are hard and soft magnetic materials, and so we can take our initially quite wide field lines that you can almost see on the screen, and poke them in so that we end up with more of them upright and parallel at the top, and we can do that with a big old chunk of iron. Iron likes to be magnetized. It's not so fussed by staying as a magnet, but it likes to be magnetized. So my field lines, if I put a bit of iron there, will go into the iron, and I can direct them around in almost any shape that I like through the iron and poke them out somewhere else. So here is the original magnet. I'll do it on the screen. There is the original magnet, and I've captured all of those field lines in the iron and brought them round onto the top. And now I have a much bigger area where I've got lots of field lines close together, and they're much more upright. The downside is, before I had one magnet, and I could stick my sample somewhere around the top. Now I have a small hole that I have to stick the sample into to be able to measure it. This is pretty much universally true. If you have some sort of open magnet geometry, the field will necessarily be weaker than some sort of geometry where you have another magnet or another bit of iron or something that it can get across to. So closed magnets are almost always stronger and more homogeneous. This is better. So this is now just two magnets. They still satisfy the rules. Field lines start at one magnet and they go to another magnet, and then they'll come around from that one back to the other side of the other. Now I have a huge space that I can stick my sample in. So the magnet that is on the, call it spin core, not I spin, the spin core is a magnet like this. So it's just two big magnets with a gap in between, and you end up with a really nice field that's there. You can do the same trick as with the iron, and we'll see in a second how that shapes the field. I've given somewhere for those field lines to go that are outside now. So by manipulating the ones that are outside the volume, I can tuck them in much more efficiently, and that gives me this enormously strong field in the middle in comparison to what I had without the iron. And so yours again has this iron frame around the outside, which is doing the job of that. So it's bringing the fields back round. We change the scale, I think is the next slide. That's it. So if I change the scale, you can see that we've not done that good a job of improving the homogeneity in there. All I've done is just increase the field strength. So you can do things then inside the magnet to try and steer some of those lines that are not parallel and are starting to spread out at the top to give us a stronger field inside. So you sometimes hear people call those pole shoes. And so you can shape the field on the inside of the magnet such that you can get more homogeneous field inside. Okay. Come on. Here are pole shoes or pole pieces. So I know that the shape of the field that I had to start with was such that the field lines were going outwards at the top and the bottom. If I make the opposite of that in a bit of steel and stick it to the front, it will help to focus the field down into the middle bit and give us a more homogeneous area. I've still only used two magnets. I've used a load of iron, which costs less than magnets, and I've picked ways to stick that on such that we end up with a really nice field at the end. Yes. I don't think I've used the word field gradient yet. The field gradient is how the lines change their spacing. So if you have no gradient, all of the lines are the same spacing. As the lines get further apart over distance, that's a field gradient.
Change in separation.
Change in separation. This is another one with more than one answer.
And this is one thing I not getting is in the previous slide with two magnets.
Mhm.
And then they are joining.
Yeah. So if you have your magnets, they're nice and close here, so you get reasonably parallel fields, but they need to make quite a long trip around because in real terms, this is quite far away from this. Although you can't see it, these lines are joined to these lines through the magnet. So I can manipulate these ones by manipulating these ones. And if I make the journey for these less long, I can fit more in here. So if I stick a bit of iron on, there's like a U shape. That's wrong.
What's the material?
Iron or steel. So if this is something with iron in, the field lines don't have to go through free space, which is difficult to magnetize. They can come in the iron, which is dead easy to magnetize, and then they'll pop round to the other side, and that helps give us more lines inside. It can be 2D, so we would do that, the equivalent of 2D. So this would be like a horseshoe. So you would have that as like the shape of a horseshoe. It works okay if it's literally a horseshoe and it's just in the middle of the magnet. If you cover the whole of the surface of the magnet, it's better. So one of the limitations of this sort of thing is you are applying 2D science to 3D things. So the more your 3D thing looks 2D, the better. So if you take a round magnet, there will be a bit in the middle where it's worked really well, and it will get less good to the edges. If you take a square magnet, it will be almost as good at all of the points across the square. And it's the same if you take a narrow strip in the middle, it will be less good than if you take a wide strip.
2 C's.
Two C's is better than 1 C.
If it's a square magnet, you would modify the building 2 narrow sheets.
Yes. Yes. Yeah. So this is an important point to make. Saturation. Thank you, me. If you think back to the graph that we had with the hysteresis, so the BH curve, iron also has this saturation point. So there is only so many field lines you can cram into a bit of iron. If your magnets are not very strong, you might be able to do this with a 1 millimeter strip of steel. Magnets we're going to build tomorrow are made out of Meccano, which is obviously very thin, and that still helps. If you take a really thick bit of steel, you will do a better job, but then it makes it heavy. So one of the things we look at when we do the simulations is making it so there is a little bit of color that's not very dark purple on the simulation, because then you know you've got a little bit of space for some more field lines if you're wrong. Okie dokie, providing a path for field lines through a soft magnetic material improves the field homogeneity. Is a stupid question because it depends is the answer. It need not necessarily improve the homogeneity, but it might. So apologies, one is very silly. Adding soft magnetic material very rarely spoils the homogeneity unless you do something which is silly. So if you took the pole shoes, which should be shaped like this, and you did this with them, you would make your magnet less homogeneous. But theoretically, as long as you're sensible with what you're doing, it shouldn't spoil the homogeneity. Yes, field strength is always good for SNR. Yes, homogeneity is always good for SNR. And the field gradient, unless you have a coil that optimizes it somehow, normally the greater the diversity of fields that you've got, the less good the NMR will be and the smaller your sensitive volume will be. Okay, so the last one is not true. Does anyone have any questions about the point that we have reached now? Good. Okay, within reason, more magnets is better. The only thing that is bad about more magnets are weight and money. But if you have infinite money and a very strong desk, you can make a better system by adding more magnets. But it also makes it hard to build. So tomorrow, my intention is that we will make at least 3 different types of magnet. One is very easy because it's 2 magnets stuck in bits of wood. One is slightly harder because it's the same 2 magnets, but that can fly around all over the place on random bricks of Lego. Number 3 is an array which is quite complicated with at least 8 magnets in, this one is harder to build than the one with 2 magnets. So the more magnets you have, the harder it is to build. We're going to have a look at some different types, and we're going to split these into 2 different families. One I will call traditional. Sometimes we call it inside in, to be the opposite of inside out, which is a unilateral magnet. But essentially they are divided by whether or not you put the sample in between bits of magnet or you put the sample on top of bits of magnet. Maybe. Go. So the simplest traditional geometry which you can have is 2 magnets, or a magnet and a big bit of metal that pretends to be another magnet. And you can change the properties of that by changing the spacing of those magnets. There will be a critical point at which 2 magnets very close together gives you an amazing field, but it may be too small to get a sample in. The more you pull the magnets apart, the less good the field gets. You can then stick on the outside of that our horseshoe, and that will improve the quality of the field that's inside your pair of magnets. Okay. You can also make that entirely out of a bit of magnet, but it will cost a fortune because you will end up having to have the direction of the magnets in different bits in different places, and that's really hard. So you will almost never see a naturally horseshoe-shaped magnet that's made out of a strong magnetic material. It will normally be bits of magnet and some iron. Sometimes it will look like it's one thing, but often it's not. Our favorite is the Halbach cylinder, and this is the one with 8 magnets, which you will build tomorrow. The Halbach cylinder takes advantage of the 3D nature now of the way your field lines are going. So if I take my pair of magnets like these, the field lines are wandering off over here in the absence of any magnetic material. So you can maybe foresee that if I were to put another magnet here that pokes this one back inside, and another magnet here that helps pull that field out, I will start to shape those field lines in a way that's quite favourable. The true beauty of the Halbach is it has no field, if you've built it right, it has no field on the outside. So we have in the lab half a Tesla Halbach cylinder that will not attract keys if you dangle them on the outside, which is very nice to have in a lab where you have people that don't know how dangerous magnets are. So the Halbachs are really nice because all of the field is contained inside. If all of the field is contained inside, you know that you have done the best possible job of making your field lines really nice inside too. Halbachs are defined by how much you rotate each magnet as you go around the cylinder. So the first one, K equals 1, every magnet points out of the cylinder. And this is the exact opposite of what we want because there is no field in the middle of a K is 1 Halbach. Everywhere that you look, there is a magnet cancelling out the magnet that's on the opposite side. So these are very useful if your goal is to attract keys from the lab and to shield magnetically something which is inside. So these are used in some analysis kit where you want charged particles to have a very straight path. It's the same kind of idea as you would want to, as we saw with the definition of a Tesla, where you are trying not to apply any force to your particles. K is 2 is the one that we are interested in. Now we are taking each of the places where our field lines are not what we want and poking them back in where we want them. So the simplest way to do that is you have 2 magnets, top and bottom, that are facing up. And you have 2 magnets at the side that are facing down. As our field lines come up and out, they have a magnet to go in and it will point them in the right direction. As you add more magnets, you get more rotation per point around the cylinder, and you get a really, really nice homogeneous field straight up in the middle. K is 3, gives you a weird field. So this is a quadrupolar field, and these are sometimes in mass spec, where you want to change the path of your particles as they go through. Use this for NMR. K is 4 is on there because it was also on the picture. I do not know what people use K is 4 for. Okay. What we care about is Ks too. So as you go around each of the steps, we're rotating our magnets so that we end up with the top and bottom up and the left and right down. And just rotate around as many magnets as you have.
If they pointed all in K1,
If they pointed all in K1, you would still have no field. Yes. If you have them in the opposite directions, in K is 2, you still have the field, which is correct, but it points downwards.
it's symmetrical.
Yes. So this comes back to your which way is north and which way is south. Doesn't matter in real terms, as long as you're consistent.
Doesn't matter in Halbach magnets. Otherwise, you have to be careful about the.
But as long as this is north and this is north, it's fine.
It's important.
But it doesn't matter if it's north and north or south and south, as long as they're the same.
On the same line.
That's right. That's right. Yes. Otherwise, you end up with the quadrupole again. Okay. Schematic of Halbach, picture of Halbach. The magnets which you use to make the very, very pretty ones on the left are exquisite. You can have homogeneities like you cannot possibly comprehend if your magnets are this shape. They cost a lot of money. These do not cost a lot of money, but you suffer at the expense that there's a big chunk in between where you have no magnet, and therefore you have bits where your field lines can escape. And so that's less good.
Sorry to interrupt.
No, not at all.
But if I put a compass inside, it can tell us the direction.
Yes. Yes.
But the same.
As long as you have a small enough compass. But if you have, or a big enough magnet. So the magnet that Martin presented yesterday, the huge one, you would obviously fit a compass in. The bore of that is 12 millimeters. And so then you need a very tiny compass.
It tells us.
But it will tell you. Yeah. And it will do it, and it will fulfill the same obligation. So that is the way that the compass needle will point inside the Halbach, which is south to north. Yeah. Okay, so these are our inside in magnets. These ones are inside out magnets. So unilateral systems are really hard to make, but the rewards are good. So I don't know why anyone would ever scan an elephant, but the example always used to be that you can scan an elephant with a unilateral magnet. It might only be this big. You might only look at this much elephant, but you can approach said elephant and scan a bit of elephant in a way that you cannot get an elephant into a closed magnet geometry. They are very, very difficult because your field is necessarily very bad, and you have to work very hard at making your field good to get any NMR on a unilateral magnet. This is the simplest unilateral magnet. There are 2 magnets on here because 2 magnets is cheaper than 1 magnet, and sticking magnets to each other is like having a big magnet. The key here is we still do not dispense with bits of iron. The bits of iron look exactly like a magnet. They're exactly the same shape, but they just help a little bit to steer the field lines back in where you want them. Always, these need to be simulated to really see what's going on. If you just grab a load of magnets, you can cut a thing that looks like a Halbach, poke them in it, and you will get a magnet that you can do NMR in. These take quite a lot more work. We now have the opposite issue. Now, I wasn't going to really talk about RF at the moment. If our field is this way in this magnet, we need an RF, which is this way or this way. This way makes more sense, which we can do really easily just with a coil. Okay, just a solenoid will give us a really nice field that works in that direction. Unfortunately, the field on these points from the surface of the magnet and up, which means that we need an RF which goes across the magnet. And you could just stick a solenoid on its side and stick a sample in, but you will not fit an elephant in the solenoid. So instead, oh, it's the lunch alarm. 5 more minutes. So you need a different type of RF coil on these, which we will look at later. But you really suffer then from a great struggle in trying to get anything useful out of those. But you can make one of those for like £10 and do NMR. If you cost in the labour costs of about 6 months of messing with shimming, it becomes expensive. If the student is here anyway, there is no labour cost. So it is difficult, a balance. Every couple of years, we go back to these and we do our 6-month stint, and then we'll go back to a Halbach. But they are magnets and you can do NMR with them. They're also very nice because at £10, you can bury them in stuff and leave them and not recover them. So this was from paper where they buried these probes in cement, and the cement cures around the probe and they're just left there. But you can watch the cement drying and see how the moisture propagates through the cement. And it's a really nice experiment, which you can't do if you're trying to bury £1,000 worth of magnet. You can do that then exactly the same as this by adding other magnets. You will make your field better. So these are some classic unilateral geometries. You have 3 magnets all pointing in the same direction, but the middle one is small. So you have lots of field lines on the outside, and you just give them a little poke in the middle with a smaller magnet, and you can make them flat, and it gives you a bigger space. You can then have your field to go across. So the NMR mouse is like this, where you have a magnet which is up one side, the field goes across the top and down on the other side. And that gives you a much easier RF coil because you're back to B1 pointing up from the surface because B0 is across. You can also do that with 2 magnets that are on their side, but the field is disgusting and you end up with field lines all over the place. But you can do the same trick again by sticking a 3rd slightly smaller magnet in the middle. And the idea of these is you can simulate it to your heart's content, but almost always there is a screw on this, and you build it and you sit and measure it and you twist the screw until you balance the field really nicely. So those are our unilateral magnet geometries. Okay. This is a long quiz. We will do the quiz and then it will be lunch.
The whole person.
Probably.
What can we do though?
Yes, we do.
Secret language.
Nice.
Well, that's not interesting.
Yep. Okay, give you 30 more seconds. Here we go. Not many to go. Okay, let's close that. Oh, one more to go. Okay, let's see how we have done. Yes, more magnets is more better. One magnet is technically enough to do magnetic resonance, though it is extremely hard. So you can do magnetic resonance with just the one magnet. So the cement one is really one magnet. That's two. It's like one magnet. The cylinder Halbach arrays can be made by placing magnets in the same direction around the cylinder. True, they won't do NMR, which is what it should have said. So you need to have them rotate around the magnet as you go to get the right one for NMR, which means that B is the correct geometry to do NMR. So A is the one with no field and C is our quadrupole. Okay. If you build them and they are wrong, you will know because they will have no field in and nothing will happen to your compass. Or when you try and do it, you end up in weird parts where you can do NMR in the quadrupole magnets, but only in very specific bits where the fields are in the right direction. Okie dokie. So that's a good place to stop for lunch. Does anyone have any quick questions before we do?
So, I was seeing talk with building such they are using some LIGO type models that they can be attached to each other. That works.
Hopefully, because that's what we're going to do tomorrow. If the difficulty is magnets are always hard to handle, and what we went backwards and forwards on the two different ways you can do it. So you can stick magnets in Lego and literally stick them to stuff, but they're very difficult to keep in one place. What we're going to do is build the holder from Lego and stick magnets in it, and that's then much easier. So we would normally build, because they want to twist. So this is not comfortable for magnets. They like this. All they do with that is they just want to flop outwards, which is easy. The Halbach, the top ones want to do this, the side ones want to do this, and they just want to twist in like a flower shape. So
Where they're arc, parts of the arc.
yes, yeah,
That's really nice.
Yeah.
So they shape the magnets in trapezoid shape.
so that you just tuck them in.
Slot
But they're easy to build. Okay, they're very hard to build beautifully. Very, very hard. Okay. When we'll be back from 1:45. 1:45 start. Very good.
Hi. Will you do any practical things in the afternoon or tomorrow will be the
We'll do all practical tomorrow. We will do semi-practical next because we're going to have a go with the software, but we won't do any building until tomorrow.
But can we follow software issues online? Because in the afternoon I have to go to somewhere else. I don't
Yes.
anything, but
Yeah, you can easily, as long as you can get the software on your laptop,
I always
then you're fine.
okay.
Absolutely fine.
Thank you.
Unless you get stuck, and then we're not here to help. Yeah, exactly. Yeah, we can send one round to you. Oh, perfect. Thank you.
Construction.
It's not
For our loop.
336.
384.
Thank you.
Yeah.
Nope, it's wrong.
336, 348. Another way around. Sorry.
That's okay.
I'll save it on my desktop. So that's a big check.
That's everything. Great. So, welcome back. We'll pick up where we left off, which is about to get into the fun bit with the magnets. So there are loads of different softwares which you can use to simulate magnets. We're going to go with one today, which is completely free. It is limited in that it only works in 2 dimensions. So as long as your magnet is like a cylinder or is the same in the 3rd dimension, it doesn't matter. It is not good if it's different in all 3 dimensions. So for example, one of the mouses has 4 magnets and each of the 4 magnets in the corners are different. You cannot simulate that on FEM. If you have one where you've got 2 magnets that are different, or 5, but they're in a line, you can simulate that on FEM. Elmer is good, and I think has a free version, and is a bit more powerful and can do 3D. FEA tool is nice because it has a MATLAB plugin. Open Foam, I think, is the Python one, and ANSYS is hideously expensive. If you have money for ANSYS, buy ANSYS, but it is tens of thousands of pounds. Same as the one that Leonid spoke about yesterday that I can't remember the name of, that's made by Dassault, the people that make SolidWorks. Again, hideously expensive, but very powerful for 3D. We very occasionally will simulate things in ANSYS because we have a site-wide license for our engineering school. Lots of universities have licenses for ANSYS, and if your university is one of those, then it's worth learning to use. The learning curve is steep. It's weeks before you can get magnets to simulate well in ANSYS, but once you have done it once, it works forever until they change the version. So we're going to look at FEM today, which is free. I don't know if we've managed to successfully install it on a Mac. We'll give it a go. So the way that FEM works is a bit like children's pictures. And you start off and you put dots where you want corners of stuff, and you join dots together, and then you tell it what's in between the lines. It's quite good fun, and it is quite powerful as long as it's only 2D. So let's try and open FEM and see how far we get. So people with Windows computers can easily install it. People with Macs apparently can install it with Wine. Excuse me. So back on the website, which will load or won't load.
But you want to try it?
No, I can see.
Will not load. So if you go to the website that had the software links on, there should now be This one should have instructions for how to install FEM on Mac. I do not know whether it will work. Theoretically, it seems plausible that it will work. And they made it sound not too difficult.
Make them text figure, so you can see the full address.
The QR code will be on a phone, so that doesn't help. So sorry, the web address is hideous.
Which one is it?
This is the bottom one. The top one's the proper FEM download.
So that's all loaded, ready to go.
This is better. We can manage these number of letters on the slightly blurry screen.
Can you share the link on the chat also?
Ah, there we go. That's easier. We'll go nice and slowly through it. Yeah.
No, that's it.
Okay, so whilst the Mac people have a go at trying to install Wine and trying to install FEM on Mac following the beautiful instructions, I'm not going to start this, but I will just talk a little bit about it whilst you try and get it installed. FEM can do magnetic simulations, which is what we're going to do, and electromagnetic simulations, which are not very good. Electromagnetics sort of need the third dimension to be interesting. So we're just going to do magnetics. It has a materials library of pretty much every material that you might want to use. If the material that you want to use is not in there, you can create custom material. So it is good at doing anything. We have never created a custom material because everything you ever actually need is in there. How does it look on Macs? Horrendous. Oh, okay, that looks hard work.
Search me down. The only thing is Windows sign.
Oh,
Windows
that's a new thing.
यहाँ पर पिछली टाइम आया है very common saying.
There are some codes in there. Did you able to download it?
Just use the page and it found.
Yeah, that looks like it.
Seeing one download page.
Your binary packages are built and supported by Wine to Mac. So then if you click on Mac, so is there somewhere where you can stick this? So if you copy this top one, I've never used a Mac before. But is there like a command line somewhere that you can put commands into?
Wait a minute. Actually, you can go 10 minutes.
No, Wine installing is not as simple as installing Wine. Wine installing is a challenge.
Yeah.
Okay.
Yeah, so
Share
let's try and distribute Mac people with Windows people and between us, we will maybe be able to do something. We will, sorry, go on.
So I think we just quickly, which one should we click here?
It's terrifying. You shouldn't need any of those.
Do I just press
So if you
that?
go back to the link. And back, and maybe go to Google, and let's just start with if you just Google FEMM, and let's go directly there. That's the one. If you go on there, it should be on there.
Okay.
And then this 64, this one 64-bit, and then hopefully, okay, this is good, and then you should be able to install that. Hopefully,
Okay, thank you.
hopefully. Let's see. We have it on some machines. Okay, so I will try and work on how you install it on a Mac. I'm convinced this is possible because there is a web page about doing it. I just need to work out how. For now, I will show you how to do it. If you have access to it or can see one, you can have a go and or watch it being done. But you will at least get to see the process, and then I will furnish you with new instructions when we've figured that out. The idea of this bit is I want you to see how it works and know how it works. In the practical bit tomorrow, presuming we have resolved some of this, you can have a play with it and work out what bits you want to build. If we haven't figured it out, it doesn't matter. You'll still know how to do this on a PC, and then I can give you some arrangements that you can do it on, or we'll have some laptops that you can try on. Okay, this is FEM. This is what it should look like. It is not an attractive program, but it does work quite well. So we're going to start off and make a new magnetics one. So you can have magnetics or electromagnetics in there. And we're going to pick magnetics because it's about magnets. It then gives us little dotty paper that you can put dots on and join the dots together. And to make it easier to do, we're going to make it snap to a grid. So that's in grid, snap grid. If you are going to build one of these in real life, we would at this stage make the grid something sensible. So if you've got 5mm magnets, maybe a 5mm grid is a good starting point, and then you know that your dots are the spacing of the magnets. The benefit of simulations like this is the units almost don't quite matter. It's the proportions that matter. So as long as you're consistent, if you have magnets that are this far apart, your measurements will still be consistent based on what they are. So a millimeter grid size, 5mm, 10mm, whatever. For now, I'm going to leave it because we're not going to build what we make. Simulations like this are going to measure the field in air, because that's what we're normally going to have our thing in. So you would normally have your sample tube and stick it in, and it will go through air to get there. So that's what we're going to simulate. And the first thing you would always do is to put a massive box around, which is going to be the air that we're going to simulate in. So you can just click dots in the corner and it will give us our air. I will try and line them up. And then we use the line tool to join the dots together, just like a dot-to-dot picture.
Can I interrupt?
Yes, please do.
Did we set the grid size to 10?
So 10's a sensible thing to set it to. I don't know what mine's actually on.
Without grid, then.
So mine's on 0.25 because mine is almost certainly in inches as well.
So where we said?
So let's start from the beginning again. If you go into edit and preferences, you can pick some units and we will work in millimeters. Then we can go into grid and set grid, and then we will set our grid to be in blocks of 10mm. And then I have a really super tiny box or a massive box. I'm not entirely sure which.
Is
Let's start again.
and you can.
There is a grid. Right, so when you're using FEM and you have started with terrible mistakes, right click will select stuff, left click will place things. So to pick the 4 dots that I've messed up, I'll right click them and then delete them. And then we can zoom out nicely and have a go with those. But it will pick whichever thing you've got selected in the top. So if you've got the dots selected, it will delete dots and select dots, and vice versa for lines. I've also placed a load whilst trying to delete these. Okay, we have a grid. Now we will put dots on the grid. So I'm just going to stick some dots in the corners. Can we remember what I even set the grid to? 10 millimeters. It doesn't make any difference. I agree. I completely agree. So here we go. So we're going to put some dots in the corners. We're going to join up the dots with a line. That's square.
I didn't even see it. It didn't look square.
And this is going to be the air that's going to be around, and that's what we're going to get the fields in. Then we're going to stick magnets in the middle. 9 times out of 10, when people first start to simulate these things, the thing that has gone wrong is there is no air. And you don't care about the fields in the magnets, you care about the fields around the magnets, which is the fields in the air. We will try and do one of these together. And in the interest of time and in the interest of how much disaster we have installing FEM, we'll do this one together, and then we'll try and work out how to install it overnight so that we've got it for tomorrow. So we're going to position first off some magnets, and we can sort of pick randomly where we're going to stick those to start with. So I'm going to have a 1 centimeter by 5 centimeters magnet. So they're 10 millimeters apart there, and then 1, 2, 3, 4, 5 millimeters apart there. And that will be my first magnet. Then I did what I thought I did 1 to 5. 1, 2, 3, 4. But I've got a 10 millimeter grid.
Do you have a 10 millimeter?
I think so.
Because mine
Yeah, I set mine manually, but to be honest, it doesn't for having a play, it doesn't matter. When you're building something that you want to actually build, then it really matters. And then you just want to make sure that it matches whatever it is you're doing. Then I'm going to leave a gap in between, and then I'm going to stick some magnets over the other side. And then go through and flick the dots to make my magnets. 2 magnets. Okay. Now I have chosen my grid poorly because I now have no dots in the middle of my magnets, which is where I need to put my material. So I'll change the grid again. This is exactly what it's like every time we use FEM. And you will see there is a third, 4th one along on that top bar is like a green dot in a circle. That's how you tell it what the materials are going to be. They're the little labels that we're going to put on the stuff.
I'm so sorry. I'm so sorry. It's really hard to see from here. That's why you want to see in the.
Put it on there. Yes, good idea. Good idea.
How did we change second time the grids?
So I went grid, set grid.
So square is this 10 millimeters.
Yeah, and then I just put it in there. So I just halved mine, so I had some dots in between. Not yet. No, I'm now going to do that. So in properties, oh, you really can't see it up there. In properties, at the very bottom is one called Materials Library. And materials library has all of the materials in that we can pick from. So I'm going to go in there and pick now the materials that we want. So we've got air, and you just drag them over to the right hand side. In hard, we can pick so sintered NdFeB magnets, and then you've got all of the different magnet grades in there that we looked at earlier. So we'll pick like an N42 or something else. It doesn't really matter. You can choose. And then in soft, I'm just going to take over iron. So I've got 3 materials that we're going to use. Some sort of magnet, pure iron, but you can pick grades of steel if you know what your material actually is. Doesn't make too much difference. And air. Yeah, so drag air. Yeah, sintered NdFeB.
Is that the drag the whole, not whole?
No. If you go into it, you should be able to pick N42 and 48.
And then the iron. So N42 is the neodymium magnet, and that's the 42 strip.
Okay, and then once we've got the material selected,
Is it any iron or any steel?
any old iron, just pure iron.
Oh, pure iron. There we go. 3 materials.
Okay, and then I'm just going to stick labels in the different things, which you can't even read on there. I should have accepted your offer earlier.
Is it possible to do the materials?
From the library, you have. So if you click the green one again on the top, then you should be able to right click them to delete them. But you need to click the dot rather than the label. That's it. And then press delete and it'll go away. That's it.
Which material did you select? I'm sorry.
No, don't be sorry. So I dragged over air.
Okay.
So you can just drag it onto the right hand window. That's it. Pure iron. And then in hard magnetic materials, in sintered NdFeB, and then I think I've used N42, but you can pick any of them. Yeah, that's it. Perfect. Okay, so we should have a thing that looks like this somewhere randomly positioned, 2 magnets with 3 green dots in.
Oh, no dots in there.
Once you have your 3 green dots, we have the little hand holding a bit of paper. The little hand holding a bit of paper will allow us to hopefully select materials, but you need to pick a dot first. So I'm going to right click on this dot and then use the little hand with a piece of paper. And from there, I can pick what material is going to go in it. Okay. If it is a permanent magnet, so a hard magnetic material, you can set the direction that the vector will face in. So magnetization direction is the angle that the arrow is going to be pointing at. So if I leave it at 0, it will point left to right, 90, 180, 270, and back to 0 again. So it's the angle of rotation clockwise from left to right. So I'm going to do that for both of my magnets, and we'll leave them at 0, but we will actually select a material. Okay, so now I've got my 2 magnets, north facing south, nothing around them. And then finally, I need to do the same for air.
Set the direction again.
Once you've got it, once you picked the material,
Oh.
it should have magnetization direction.
We've got okay at first.
No, it's there, magnetization direction.
Oh, that.
Yeah. How are we looking?
No.
Give them to it.
So if you
Why not?
it needs to be that one,
The green one.
the green one.
Okay.
Then you should be able to right click. That's it, and then you got that one. That's it. Perfect, perfect, perfect. Yeah, it's really weird. It takes a long time to get used to. Once you can do it, it gets quicker.
Both the same orientation.
Yes.
Okay, yeah.
So this is the drawing bit done. And make sure you've got air. Before FEM can do anything, it has to save the file, and if you don't save it, it will moan about it, but we'll save it now. Yes, please do.
What's the relation between air and magnetic field? If we don't have air, what will happen?
Nothing. So FEM will only simulate the fields in air.
But you said there is no relation between air and magnetic field.
Not reality.
Air is very hard to magnetize, but we want to measure the field lines, and you need the material for it to put the field lines in.
Actually, we are magnetizing the air.
Yes, somewhat, but a tiny little bit. Yeah. So once we've saved it, we can do the exciting bit, which is to turn all of the bits on here into tiny triangles. And it's going to go through and work out the field in each of the tiny triangles. Okay, so each of these tiny triangles is a finite element, which is the finite element bit in FEM. So you just need to click the little yellow triangle-y thing on the bar at the top, and hopefully it will mesh.
You can get some money.
You need to save it.
Yeah.
So file, yeah, that's it. And you can just give it a name. And then, yes, there we go. Success. Yes, please.
Oh,
Ah,
so actually click this button, but it's not happening. Anything, just after.
so to get that one to work, you have to have selected with the right mouse button each of your dots. Okay.
To do the times and everything.
Yes. So when you are doing finite element simulations, FEM is wonderful and it just does it, and most of the time it's right. But you can pick different densities for how many triangles you have. The more triangles you have, the longer it takes to run, but the more accurate the answer. If you don't have enough, you can have an answer that looks accurate but is utter nonsense. 99 times out of 100, FEM gets it right to start with, and it will put more triangles around corners because they're hard. It will put more triangles between magnets because it knows where the field's going to be. Once you have pretty triangles, you can click the twisty wheelie cog, which is next to it, and it will actually do the calculations in each of the triangles. It will do the calculation in each of the triangles.
Is it being finite differential method?
Yeah, PDE, partial differential equation finite element modeling method. So have you cogged yours?
Yeah.
And yours just went like this?
Yes.
Yes, because that's how long it takes.
To inside the air box or and
No.
so
We cannot solve the problem.
Interesting.
But
Because of the grids.
because I
it
couldn't
looks
also
okay.
arrange the grid part. I tried it, but
Yeah, no, that all looks fine.
okay.
Why doesn't it like that then?
Should I close and?
It looks fine. No, it looks okay. You can just click this one.
Mhm.
Nope. How weird. Just click it again and let's just see. Yes, please.
The mesh, which will be calculations.
Weird.
So when we click the cog, it's done the calculation. You know, obviously.
Maybe we have too much notes.
Oh, it looks good. It looks good.
Yeah, I will close it and open again.
No, it looks okay. So if you okay that and just go analysis, maybe it's operation. It's not that either. What's in problem?
Okay.
Millimeters. Nope, that's weird. So this is all fine and should work.
Okay, maybe I should close and open it.
Maybe.
Make it.
Maybe.
Right.
I'm all right at the minute. Thank you.
We are starting again.
Okay, good. But yours has worked.
Yes, they're working. Yeah. I know, it's cool.
Yeah.
Yeah, well, let's see the result. Do we have to do anything else before we can?
No.
Why won't yours?
I don't know. I don't know why mine isn't even. Oh no! Look, I've got the same as Esma. Mine's decided it's not going to solve it. It's just mine's hiding behind.
Your grid is a lot bigger than, I think I did a much bigger area. But I can't imagine. Oh, it doesn't make it, no, it shouldn't make any difference. Every, well, it just has slightly different magnets. That's all the size of it. That's all.
How bizarre. I don't think I've ever had it not be able to solve it.
Why would you've got a mesh, it's happy with everything.
Yep.
You've got your closed shapes.
Yep.
Into the box again, or
That's what you're meant to do, but it's a faff.
okay.
But it has worked.
It does work.
So it may be cross because of how little stuff there is in there. I don't know.
No.
Instead of just having a box of air, which relies on you being far away from the magnets, you can use one of these automatic boundaries and it will work out roughly how far away it needs to be, and it will gradually decrease it so that it can predict what field lines will be like if they go off the edge. You can replace your box around with one of these if you use the very, very last button on the strip at the top. Mine has then worked. Yours was working to start with anyway. And once you've done that, then you can press the little cog and absolutely nothing will happen other than the bar will progress and all is well. To view the results, you need to click the spectacles, and then we will see the field lines around the magnets. Okay.
We've got the same, but his.
But mine's stupidly off to the edge.
Yeah. So it looks roughly the same. That's some weird. Because our
Yes, I
we're
missed,
not.
but I missed the first. At least it's
Okay, excellent. Then if you press the glasses,
okay.
yay. Very good.
Yeah.
Okay, so now we have our field lines, and you can see the field lines look surprisingly like the simulations that I showed you earlier, because they were done in FEM. If you want to have pretty pictures, you can then click the stripy coloured one, and you can show a density plot of flux density in Tesla, and you can pick in there the range that you care about. So maybe we'll go up to half a Tesla, and then it will colour that for you too. And that will then give you the field intensity as a colour. That's it. And then you need show density plot. That's it.
Okay.
Perfect.
Since our B.
Correct. Correct. So between us, we all have different magnet spacings and different magnet thicknesses, and that's why we've all got slightly different fields. Okay. We can then play with this a bit more easily now it's actually working. And so we can, for example, go back to our original drawing, which is down at the bottom in the little tabs. And I can add around that some iron.
What are you going to say about it?
Yes, thank you. Well remembered. And I realized before when I was walking up that there's a bit that I've forgotten to tell you. So if you build a magnet, and you can play with this, and FEM is quite nice for this because you can stick stuff in random places and see what will happen without having to build it as magnets. On the picture here, I drew best practice, which is to have a gap here. If you stick this bar all of the way up to the bottom of the magnets, it's just as easy for these field lines to hop into this as it is for them to cross over, and you actually ruin your field which is why that question was stupid earlier about whether or not iron makes your magnet better. So this gap should always be at least a radius of that magnet. And if you bring it closer than that, then it will mess up the field. So when you see these often, it might not be obvious in the box. So like the one that you've got downstairs, that extension goes this way rather than that way. So the magnets are sort of inside the box rather than all the way up to the edge, just to stop that field hopping out. So with that in mind, we also need down here a point like there, point like there. Some corners on the go, and then we just do exactly the same thing, join it all together.
Yeah, we listen to this now. Sort of a C around it. Okay.
Yeah, so I've not followed my own instructions here because I put the dots in the wrong place, but
The gap is too small.
my gap is too small. Now we will see what happens when you have too small a gap. And then I'll make that iron. And then we just do the same thing again with the dots. And we solve it, and it finds it a bit more tricky because there's more going on. And then you can see on here, because it's too close, it's sort of gone wibbly at the bottom. Okay. But that is the process by which we use FEM. There is no cost to FEM, no magnets get used, no materials get wasted, so you can build anything that you can imagine in FEM and see whether it will work. When you are doing something new, it is always a good idea to start in here. And you saw the two talks that we had yesterday, where magnets were built. There was a field simulation before anything was constructed. So it's always a good starting point to make sure that what you're going to build is going to work. It is also a really easy way to optimize where your magnets are. So I can now play with that spacing quite easily and work out where things should be. The final thing is FEM also has a toolbox for MATLAB, and you can move stuff around automatically. So we do sometimes simulations where we change the spacing of the magnets and look at the field profile, which is useful. So let's see how we are looking.
That's a simple question. How can we delete the things?
So if you right click, oh yes, you have many. If you right click, so if you use the selection thing up here, you can drag a box around them probably, and that will select the labels, and then you can press delete.
Yes, but not for this one. Just it's deleting the dots. But how about this none part?
Yeah, so as long as you've got the green button selected in there.
No,
I don't think it selected it.
it's better to
So
go
try
to
again.
start.
Never give up.
Then we miss the sunrise. Then we go.
Then the dots. So if now, for example, if you put a dot somewhere and you don't like it, you can right click it and then press delete,
Okay.
and it will go away. If you have a dot and a line and you want to delete the dot, you have to have the dot selected and not the line selected. So it will only select whatever you've got
So I
picked on the top.
first I need to like make a block.
Yeah. Or you can use the that thing. Yep. And just okay that. So that, for example, will give you the field, the optimized boundary condition around what you've got drawn. So once you've drawn your magnets, you can stick that on after. For now, you should hopefully be able to undo that.
Then I do one more thing. This is not like for example, if I put this dot, if I make this a magnet.
Oh yeah. So get to the end of that. That's a good idea. That's it. And then you just want one label, so one of the green, and just pop one in the middle, and then right click it, the dot rather than the label. That's it. and then you can use the little hand thing, but you have no materials at the minute. So you need to go properties, materials, library.
No, no.
You want the library, materials library at the bottom.
Close it. Just close it. Properties. Properties. Material library.
And that's it.
Okay.
Yeah, they're your boundaries. So then you can drag over air and then,
Delete this one?
no, leave them. And then if you go into hard magnetic materials
Yes.
and then sintered NDFEB, then open that one out. That's it. And then you can drag over one of the magnets. That's it. Then if you okay that, oh, touchscreen. Then if you go into the hand thing, this one in the middle, that one, yeah,
Yes.
then you can make that the
Okay.
NDF, the N42, and then okay that, and then try and simulate and see whether it will run.
Which one?
Oh, you need to save it first. Oh, you need to save it first before it will let you run it. So if you just, yep. And then,
Like QH.
Just say failed.
yeah.
Example.
That's it. That's fine. And then the yellow one, because we didn't tell it was air. So you need to, so that's what happens if you don't have air. So if you pick a green label and pop a green one just in this bit here somewhere. Yep, that's it. A green
Yes,
one,
just
and then
click
just click once on the, that's it. And then right click that one. That's left. So right click that one and delete it.
Oh, no.
That's left. No more left. Right click it.
Now delete.
That's it. That's it. And then one more. That's it. Then right click that one.
And the same place.
Yep. And then you can do this left one. No, that's it. And then make that air.
This one.
Just, you're not
Yeah, you want that one as air.
here.
Oh,
Okay.
We're down the
Go down,
bottom.
yes.
That's it.
yeah.
Okay.
Then okay that. Then the yellow one.
Oh, thank you.
There we go. Then the cog. So you can okay that.
Okay.
Then the cog.
This one?
Yep. Yeah. And then the glasses.
This one.
Yep.
Oh, thank you.
Okay.
Success.
So we are successful. That if I build a magnet,
Yes.
like the way
The back.
you do.
Yep.
And it's and I put like if we assume we have a campus,
Mhm.
then when we like vertically insert it,
Yes.
it gives us that direction that
Yep. So we would pick those directions based on where the magnets are facing. So when you put the label on, you can pick the direction that the magnetic field is facing.
okay.
And then once that's in there, it will know and it will do the simulation.
What's the nature of this? What's the nature of this?
So those are the field lines that we saw on the slide at the beginning. And they don't have arrows on, but you can, if you click the arrow one on there, it will give you field arrows. Yep. And then you can just okay that. They might be enormous. They might be too tiny to see. Click it again. Let's just see if we missed a bit. You need the vector plot type. And if you make that B, that's it. And okay that. So now you've got arrows showing you the direction of the field. They're quite small. Then if you click the colored stripes and show density plot, that's it. And then okay that. And then you have the fields around it.
Did you choose the test the value of the magnetic field of the magnet? You choose the material of the magnet, but you didn't choose how strong the magnet.
It knows that from the grade of the magnet.
You did material you are talking about.
Yeah.
But is it just about the material or?
Yeah, because the grade of the neodymium tells you how strong it is. So that's built into the library.
Can we have same material but different strength magnets?
Yes, so that's the difference between N38, N40, N42, N44, N40. They're all neodymium iron boron,
Oh, okay.
but they're different strengths.
And once when we complete this design, then we order the magnets.
So that's what we would normally do.
And if we have a.
What we normally do is we look through the catalogue, pick the magnets, simulate the magnets, and then if it works, then we buy them.
Then we buy.
Yeah, so we never buy anything
Okay.
unless that's been done.
That, okay. Similarly, if we already have a magnet.
Then we stick it, then, so we do lots of these where we've got, there's magnets that we've found.
Final result of that magnet.
Either with a good Gauss meter, or you have to find the data sheet. But that's the point at which you need a reasonable Gauss meter. You can have a guess with your phone, with the magnetometer in the phone, but a Gauss meter is the only way really to know.
Doesn't matter if you put a line in here or.
So if you put a line in there, you'll need to put a label above and below it, because they're two separate regions. If they're one block, then you only need one label.
Iron, right?
Yes, yep.
I was getting using a smaller size, maybe that's why.
Yeah, maybe.
Also, I am wondering that you are, you put a lot of circles. Why?
So the circles are what you're meant to do, because it's called a graded boundary. So each of the circles has a different permittivity. And so what happens is, like on mine, where the field line has hit one of the circles, if it's just a square, it gets confused and it tries to force it back in. But the circles allow it to extend out to where it probably would in real life. So you can do those if you look. Oh, come on.
This happened.
Yeah, so that's what was happening on mine, and it hides that it can't solve it behind it, which is helpful. But if you delete your box, you can leave the dots. No, leave the, yeah. That would be the left button.
I know.
Yeah.
I'm surprised that you didn't say.
That's it. And then do the proper boundary condition, the cycles, and that's fine. Yeah. And then try and see whether that will solve. That's okay. It doesn't mind them.
No, it does.
You mind them, but it doesn't. It doesn't. It minds the lines. It doesn't mind the dots. Yeah, so each one is so mu1, mu2, mu3, mu4, mu5, mu6, mu7. So each one of them is a different permittivity as it goes out.
Yeah.
Yeah. Let's see the results. If you use use the bottom one, and then you can drag a square around it.
No, I will do it in my way.
Yes, same question. Is that normal? How can I say? I don't know, but
That is perfect.
I can see in here. How can I?
So if you go back to this one and just click the view.
Oh.
So it sort of, when you do view, it opens it again and shows you the new one.
Okay, but in here, our circles are outside of the box, but yours, the circles are inside the box.
So I think it's just because your geometry is closer to correct. Oh, that's mine.
Yeah.
They're closer to correct, whereas on mine, I've got this far too close. I don't know, but no. Interesting.
It's different.
Yeah, it's interesting. It's because my iron is thinner than your iron, and my magnets are thinner than your magnets. So it's just that I've managed to get that field line, and you've not quite got it. But it's not because it's that much different. It's just mine is just above it, and yours is just below it. But that's mine.
Okay.
But the bit in the middle is quite similar. So your field is nicer than mine because your magnets are bigger. And then you've got a bit more of a gap at the bottom, so you've got less of a wobble on the bottom. But yeah, that's why I've got that field line on there, just because you've got, so your one comes in and hits back into the top, whereas mine was just that little tiny bit further out.
And what is the biggest box? Why do you put that in this?
So this box is because we're normally lazy and it's quicker just to put a box on. The circle one is what you should really do. So that when the field lines hit the circle, it will continue to try and shape them as if you had an infinitely large box. Whereas if they hit the edge of this box, so like this field line here without the circles would go and struggle to work out what to do. So you don't actually need that box on if you've got the circles.
And I can meet.
Yeah. Okay. This is FEM. So apologies again to those of you that have Macs. Still don't really understand how we make it work on a Mac, but we will try and resolve that. If you can have a play with FEM, it's useful and it's good for having a practice before you start to build stuff. At the point at which I thought that would be easy to achieve, I was going to get to play with the spacings and then try how back, but I don't think anybody needs that in their lives today. So instead, we'll wrap up the magnets bit with a quick look at how you actually then measure the magnetic fields once you've made your magnets. How you approach this depends on how much money you have and how much equipment you have already. We like these. They are priced in such a way that they can normally be bought with a little bit of money that's left at the end of the year. But they are still expensive, but they are expensive because they are very, very good. So these will measure fields down to single digits of Gauss, and they will measure up to, I think these go up to 1 and a bit Tesla. So they cover a really wide range. They're very accurate over that range. And you plug in the probe, you turn on and you poke it and it will give you the field. So they are really, really easy to use. So those last Friday were £1,400 or 33,000 Turkish lira. If you have the money, buy one. If you don't have the money, you can do it for €3 to €5, as long as you don't mind getting your hands dirty with some electronics. So these will output a voltage which is proportional to the amount of field present. They are very good, but your measurement is only as good as whatever you plug into that. So if you put it into a horrible cheap Arduino, you will get a horrible cheap answer. It's good enough. The message with the whole course is this is easier if you have one thing which is good. So if you have a good console, it's really easy to build magnets quite quickly. If you have a good magnet, it's really easy to build a console quite quickly. If you have a really good Gauss meter, you can easily make the magnets work quite quickly. But one of the things, if it's good, is easier. If you have a friend that has something that's good and can borrow something that's good, which is what we did to start with, you can quickly make progress. If you try and build a console, a magnet, and a Gauss meter, I suspect you will struggle. So making one of the things good is always worth it. The halfway house, which is still much closer to this, are these little modules which are about £10, and you can buy them as this board, but that is a digital reading then. So the conversion is done on the little board, and then you can stick it into anything that can read a digital signal like an Arduino, and it will give you the value of the field in 3 axes. Mike made a array of those in like on a stick and uses them to map the magnets, really big magnets, so just moves them around and you can map the whole of the field, which is really nice. So again, you still need something to read it, but for €10 for an Arduino, it's much better than £1,500 for a Gauss meter. Okay, that's magnets. So hopefully you know what magnets are. We understand a bit better how to use the conventions of the field lines to play with what we want to do. I think between us, we can use FEM, although it was a challenge. We looked at some different designs, open and closed designs, and how we can simulate and measure them. What time do we want afternoon coffee before I plan? Want to go now? Okay.
Normally, we are sticking our magnet into the metal, so we are magnetizing the new magnetic thing magnetized. So it will become a magnet.
For the iron or for the not iron?
For the one we use in the lab. They are iron magnets.
The iron hold, iron shoe.
The black thing, yes. They will be magnets.
Oh, yes,
For you.
yes.
And it will.
Yeah, so the whole thing is a magnet. Yes.
So no, it's not the.
Yeah, the blocks around the outside turn into magnets with the magnets in. But that's why is to bring the field round tighter so you get nice field lines across.
The magnet doesn't come from
It's fully enclosed in the.
Let me put the question like this way. This is a magnetic thing, and if I put a magnet in it, it will stick.
Yes.
And at the beginning.
And then this becomes a magnet.
And this
Correct, because it's a soft material. Carry on. So that's a soft magnetic material.
Always touching with a magnet. So it
Yes.
stays as a
Yes.
magnet.
Correct.
As long as they are touching.
Yes.
So does it affect magnetic field over time, like?
Oh, no.
3 months?
No, no.
We are increasing our magnet size.
But you're actually not. You're increasing the magnet in the gap, and you're not gaining field lines. You're just putting them into the iron. That's right. Yes, conceptually, that's very important.
You're moving, not.
Yes, you're not changing them, you're moving them. No free energy. Right.
Keep thinking. Just don't stop. Yeah. One day.
Yeah, perfect. 320 back.
Yeah. So you're on the mic.
Perfect. Thank you. Okay, so let's start again. Final session of today is going to be RF coils. The whole process of the process of the RF coil is really easy. So we can take a bit of wire and do this, and we've made an RF coil. But unfortunately, we have another hour of PowerPoint to go because there's a little bit more that goes with it than just to the coil. So if you can probably do the next 2 slides, I guess, because I think the next one will be, let's see. Yes, I suspected the next one would be not anything.
Yeah.
Yes, perfect. So we're going to have a look at what an RF coil is. We're going to have a look at some tuning and matching and impedance matching, which will be the long bit. And then we'll have a look at how we analyze the coils. So the RF coil's job is to transmit the signal that we need to rotate our spins to our sample. And it's going to collect the signals back from the spins as they process in it and induce the voltage in that coil. The closer your coil is to your sample, the easier that is. So there is a thing called fill factor, which is the percentage of coil that has your sample in. You can theoretically achieve 100% fill factor if you immerse your coil into a liquid. But at any point you put your sample into a tube, you start to lose fill. 100% fill factor feels like the best thing. But actually, right at the edges of the coil, you start to see some strange things, and the field is not homogeneous near the edges. And actually, having your sample in the best bit of the field is always better than just arbitrarily completely filling the coil. So on the left are a load of coils. They are pretty much all a form of solenoid, be them flat or long, but they're fundamentally a bit of wire. So let's see what's on the next slide. Okay. Let's start right at the beginning. This is a piece of wire, and the piece of wire conducts electricity with this kind of pretend flow of electrons along the length of the wire. So whilst it's very nice to think of the electrons traveling from here to here and zooming around a piece of wire, it's not really what's happening. But it works so much easier as an analogy that we will stick with it steadfast until the end. These are like pipes, okay, with water flowing through them. The electrons are the water flowing through. And if you squeeze a bit of the tube, it gets harder for the water to flow, which is like resistance, which is one of the electrical properties that we're interested in. Voltage is the amount of force with which the water is being pushed through the pipe. And the current is how much water is going through. Okay, so these are our 3 things that we have which define electricity in a wire. Voltage is the current times the resistance, and this is the kind of full law that governs how electricity flows in a wire if it is happening constantly in one direction. This is not possibly further from what happens with an NMR coil. And so there is a little bit more complicated stuff which we need to do first. So this is our kind of basic model for straightforward current flow in a wire. So if we can have the next slide, which just has that relationship on the bottom. There we go. So there are 2 types of flow of current, AC and DC. Alternating current, which is backwards and forwards, or direct current, which is in one direction only. So in our water pipe, our hose on the left, we have DC. All of the water flows in one direction, and life is very simple. And these are the sorts of things that we charge phones with and batteries have. On the right-hand side, the water in the hose jumps backwards and forwards and backwards and forwards. It's still transferring energy whilst that's happening, and that's what makes it useful for us. But if you look at a plot of current over time, against time, it goes up and then it comes down and then it comes up and then it comes down. So positive to negative, positive to negative. On the left, life is very simple. on the right, life is very complicated, and it gets progressively more complicated the faster you switch that backwards and forwards. We are going to switch that backwards and forwards more than 1 million times a second, and that makes it very difficult, okay? So next slide, please. So in electronics, we have a set of components which are called passive components. And passive components are just extensions of that pipe. So a resistor is the equivalent of squeezing the pipe in that it restricts how easy it is for the water to flow through the pipe. And it will basically kind of try and push back and stop the flow. Capacitors, which are in the middle, allow us to store water or charge. And they are going to be one of the most important things that we're going to look at this afternoon. The simplest capacitor is 2 bits of metal with a gap in between, and the charge builds up on one of the plates. There is a point at which you can store no more charge in a capacitor, and then it will potentially start to flow again. So they have a particularly interesting behavior. The final one is an inductor, which you'll notice looks exactly like the RF coils we have already looked at. That is because RF coils are inductors. Inductors do a different thing entirely. And just like with our RF coil, if you put a current through that, you will get a field inside the coil. It is difficult to create that field, but it is difficult to collapse that field too. So instead of storing charge like a capacitor, they store energy as a magnetic field inside. So if you can just click once, hopefully we'll get some definitions under the bottom. Very good. So this is V is IR still, just like we saw on the hose pipe. Voltage is current times resistance. The capacitor for DC is basically a broken wire. So you've got 2 plates, they are not connected, and DC will not flow between those 2 plates unless you go extreme and manage to break down the air in between. But the current should not flow between a capacitor. Our inductor just looks like a wire. Stuff gets weird if we then have this zoom backwards and forwards. So the next slide should be AC. And now we have this storing charge and we have this storing energy. Capacitors, just like the resistor, resists the flow of current. The capacitor resists a change in voltage. So capacitors do not like you to go up and down, which is good because we're doing AC. And just the same, the inductors, which are storing energy, do not like current to change. So they will try and stop you as much as possible changing the current, because when you change the current, it needs to change the field and it doesn't like to do that. So these are our 3 components, and AC is what we're looking at. They are defined by capacitance is the amount of change per unit time that you can do. And the same for the inductor is the change in current per time is inductance, or L. I don't know why it looks like a lowercase l. Next one, please. So conceptually, we're going to do a thing now called impedance matching. Impedance matching, I used to think, not today, is one of the most conceptually challenging things that we do in electronics, but I believe I have a nice analogy which will make it not complicated, but we will find out in 5 minutes time. So if you start off with our pipe and you flow water through the pipe, everything is going well and it's just like it was before with the DC. I think the next slide we want now, we do. If now I have this one pipe and I want to collect water at the other end over here somewhere, and I stick a stupid tiny pipe in the middle of it, I will not collect much water over here. My wife said that however I arrange these, I will never collect any water over here because it will just pour out here. So we're using a very stiff gel. And if you click the next slide, a purple gel should hopefully appear, which can be pushed through the pipe, thus the analogy continues to work. This will then flow from here to here. It's just thick enough that it doesn't fall out immediately, but it will start to drip on the floor over here somewhere, so that a bucket over here will just collect what flows through the green pipe. Big pipe into small pipe, very little water, very big puddle. Next slide, please. Not very much, mess. bad. Okay, this is badly matched. If we make the green pipe slightly larger with the next slide, we will collect more stuff over here and we will have a smaller puddle. If we go one more slide, the pipe should be the same size and we collect all of the water over there and there is no puddle. This is all that is happening with impedance matching. It sounds much more complicated when you do it with the maths, but all that is happening, if you join together two cables, two systems with different impedances, and we'll look at what impedance actually is in a minute, you will lose energy. If they have the same impedance, you can transfer all of your energy from one side to the other side. So we're going to spend now quite a while doing impedance matching for our RF coils. And that's all we're trying to do, is we want to get all of our energy from our console into our sample and into our RF coil. Is everyone conceptually happy with what we're trying to do at least? Very good. So I think the next slide will say source impedance and load impedance. The source impedance is where our signal is coming from. Our load impedance is where it is going to. And the next slide will maybe give us some symbols. Okay, so impedance is represented by the letter Z, ZS for source, ZL for load. The definition is you get maximum power transfer when your load impedance is the same as the source impedance. And that's what we're trying to achieve with all of the tuning and matching that we're going to look at next. Okay, thank you. The definition of impedance is that it is the effective resistance of an electric circuit or component to alternating current arising from the combined effects of ohmic resistance and reactance, right? Load of nonsense. Click the next slide, we'll lose some of them words and it will maybe start to make more sense. So impedance is resistance to alternating current from resistance and reactance. I think we can do one better because we still need to deal with reactance, right? We've met resistance, it was our resistor, it's constricting our slide, our tube, our pipe, thank you, but reactance is new. So on the next slide, we will have a definition for reactance, which is something like resistance for components that don't have resistance, which is still kind of stupid. But if you click once more, it's actually just resistance for things that don't have resistance. When you have AC and it's flying backwards and forwards, there is still a force which is trying to stop that happening, and we just call that reactance. Resistance was already taken for DC, right? So these are the types of coils which we are going to look at today, and they are broken up into two families. On the left are what we call surface coils. So these are when you have your sample on top of or underneath your coil rather than inside your coil. If you have your sample inside your coil, we call them volume coils. Okay. Surface coils come in all sorts of shapes and sizes. Volume coils come in all sorts of shapes and sizes, but these are pretty much the only ones that you will encounter, I think, really ever. These are literally a hoop of wire. So this is a surface coil. And I can just stick my sample on top of it and do NMR, okay? If I pull it out very slightly, it becomes a volume coil, and I need to stuff my sample inside of it to achieve NMR, right? But they're literally just different arrangements of turns of wire. On the next slide, we should have the directions of the fields. So our hoop and our square hoop have fields which go into the page. The bottom one, which is a double D coil, sometimes you see these as squares, which are called butterfly coils, has a field which goes up the page. So it comes out of, it's like two of these really. It comes out of one and into the other. So you have a field that's upwards. And that's the one that we would want if we were trying to do it with that single magnet. So if you've got your single magnet and the field is that way, that's the coil that will give you a field 90 degrees to that. The volume coils then are two of those, just like the two magnets. If you stick two coils next to each other, the field will go between them. These are not very good, but they have some useful applications. The one that we use a lot in MRI is the bird cage coil. And the bird cage coil is useful because you can fit a human in one end of it, but the field goes across the coil. The solenoid is the best coil, but if you fit a human in a solenoid coil, they can't fit into the scanner because the field is along the length of the scanner. So the birdcage coil is used a lot in really big scanners. We are going to look exclusively from here on in at the solenoid because I cannot conceive of a geometry of magnet that you would want to build if you have not built MR probes before that would not work with a solenoid, okay? Once you've cracked solenoids, you can do the others, and they're all extensions of solenoids in one way or another, but the solenoids is one that we're going to look at. I think the next slide is probably a green circle around the solenoid, so we can do the next one. If you like maths, if you like physics, you should read this paper. It is a joy. If you do not like maths and you do not like physics, I will summarize it on the next slide. There is lots of maths that says this is the best way to make a solenoid. If you take your wire and your wire touches the next bit of wire, like this, I don't know whether or not you can actually see that. If your wires touch in your solenoid, you get an okay field. If you separate your wires by the diameter or the radius of a wire, you get a really good field. And the tiniest of change in that really makes an enormous difference in whether or not NMR is good. When we make coils tomorrow, we won't do this. If you're trying to do a really good job, you should optimize everything to give you this kind of spacing on, off, on, off, on, off. And it's so easy to achieve because you wind your coil with 2 bits of wire and then you unwind one and you end up with the spacing of the wire. So it gives you a really nice solenoid. The problem is, in order to tune and match our coils to a frequency as low as we want to, you would need wire which is so tiny that I don't think it's windable by hand. I think it needs to be wound on a coil winder, which is not what we're going to do tomorrow. So there are 2 relationships which are important from this. We're not going to go through them in any detail. I just want you to see a couple of things which are important. So B1, which is the strength of the field inside that coil, is proportional to the number of turns that you've got on your coil. So the more turns that you have in the coil, the stronger the field will be. But you need lots of turns over a given distance. So if I have like a coil like this, I'll have a rubbish field in comparison to having loads and loads of turns over a certain distance. So we try and maximize the number of turns per length that you can fit in whilst keeping that spacing if possible. However, every time you add a turn, you square the number of turns and it gives you more resistance, and resistance is the enemy of the RF coil. The stronger the resistance of the coil is, the harder it is to push the current through and switch it backwards and forwards, and the less efficient you can transfer that energy, with an exception which we'll look at in a bit. So I think that's everything that's interesting on there. This is absolutely nothing to do with coils, but I love it as a conclusion. So bearing in mind our scanner, which is considered by today's standard is a very low field MRI scanner, runs at 65 megahertz. The conclusion of this paper is that you should never try and do MRI of a person over 10 megahertz. And they mean it, like it's serious. Do not do this, it's really hard. So when you are writing conclusions of papers, be careful about claiming things outright to be true. Next slide. So we are going to look now at tuning and matching. We hopefully have an idea of what our RF coil is and what it's doing. We know about impedance matching, but now we need to kind of marry all of these things together. So tuning and matching is the process by which we achieve this impedance match. Now, hopefully, if you click the video, it will have sound. Okay, so these are wine glasses, and rubbing the top of a wine glass makes it make a beautiful noise. If you like it, might be a horrible noise if you don't like it, because of resonance in the glass. It's probably enough of that. Thank you. Thank you. And then on the next slide, we should gain our picture of a swing back from our conceptual discussion earlier. Yeah, because of resonance. So exactly like we talked about earlier, we need to have everything on resonance in our system. Our RF coil is the same. The glass resonates beautifully, not because they're going into the glass, which is a thing. You can break glasses by making the right noise into them. But they are just hitting that with some random energy, and it is vibrating at exactly the right frequency because it is resonating. When things resonate, you get enormous amounts of energy for very little energy in. If we can make our RF coil resonate, I can tickle it very gently from the console and get loads of energy into my system. If it is not on resonance, I have to hit it really hard to get it to transfer any of the energy into the sample. Is everyone happy with this so far? Good. Next slide then. Oh, again. Yeah. Okay, so we are trying not to do this to our coil. We are trying to do this to our coil. This is the goal for tuning and matching. If we resonate our coil, we can make it so that whatever is going on over here will transfer all of the energy into the coil. Yep, next one, please. So we have our console on the left. We have our RF coil on the right. We want to do this big arrow of energy transfer, not the small arrow of energy transfer. Okay, next one. Okay. There are at least 6 ways I can think of off the top of my head to solve this problem. I think in practice, we only ever use one. If you are building probes which are low frequency, there is really only one which sort of works, and that's what we're going to look at now. So on the next slide, hopefully, we will revisit our beautiful components and start to see something interesting about their behavior, which will allow us very easily to make them resonate. So our capacitors are resisting a change in voltage. Our inductors are resisting a change in current. If we go to the next slide, if we increase this voltage in our capacitor, which is going to store that charge, it's going to desperately try and stop me increasing the voltage in it. Okay, so we'll see this as a characteristic curve, which is hopefully the next slide. Yes, again, an exponential. If I connect a capacitor to a power supply, it will charge like this. Okay, it charges very quickly to start with, and then it gets slower and slower and slower and slower until it reaches the voltage of the power supply. On the next slide, we can see that if we have that charged capacitor now stuck into our inductor, it's going to try and discharge the energy that's in that capacitor into the inductor. But the inductor does not like changes in current. Okay, and it is now going to be annoyed that we are trying to change the current in there and do its absolute best to push back. And the next slide should hopefully be it pushing back. The capacitor now dislikes the fact that we're trying to change its voltage, and it's going to resist or react to the change from the inductor, and it will go back again. And then this gets cross because it's being charged from the capacitor and it doesn't want to change the field, and it will go back again. And we can do this for 100 more slides, but Amor said we should not. So instead, we will look at the graphs. If you take a charged capacitor and you plug it into an inductor, this will go on for a long time. Okay, until resistance of wire and things takes over. Eventually it will run out, but you can actually, it's a fun experiment to do if you've got an extremely high impedance measuring device. You literally charge up a capacitor, stick it on an inductor, and you'll get this beautiful oscillation. This looks a lot like resonance because this is resonance. There is one frequency that will happen at, and it is determined by the value of the capacitor and the value of the inductor. And the relationship is 1 over the square root of the value of the inductor and the value of the capacitor. This is called a tank circuit. it's fallen out of fashion a bit. But if you speak to old NMR people, they will almost always refer to tuning and matching as a tank circuit. You can think of it as storing the energy that we've got there, and in a way that is extremely efficient. So if I apply on this side, this frequency, so I've picked my inductance and capacitance to give me a frequency which I care about, we can really, really effectively resonate that circuit. Okie dokie, next one, please. It's wrong to say that before you build any NMR probes, you should buy and read this book. But before you build any probes, please buy and read this book, okay? Or find it in the library because it's quite expensive. There is no book which covers better all of this stuff, okay? And it really is very good. It's quite old now, but it's still extremely relevant. And if you like books, it's nice even as a book. So I really can't recommend that highly enough. Anyway, I have stolen the illustration from it on the left, because this is the circuit which we had before, which was resonating. And I've stuck another capacitor on the front. And now it has a connection that I can connect to my spectrometer. We tweak our resonance a little bit. So now instead of being C, it's the sum of both capacitors. But that gives me a connection to my spectrometer. And the next slide will reveal that that is our RF coil, okay? That is literally the connection of 99% of spectrometers in the world to RF coils, a capacitor in series and a capacitor in parallel with the coil. We can then pick the values of those capacitors. You're kind of stuck with the value of the inductance of your coil based on how you've wound it, such that we can make that system resonate, and that makes it really, really easy to put energy into our sample. Does anyone have any questions about that so far?
So which age of coil matters?
Yes. Everything matters. The spacing matters, the number of turns matters,
Yes.
The thickness of the wire matters.
What the number of turns matter?
Let's see if it's on the next slide. I don't know if I took it out. I took it out. The inductance of the coil is dependent on the number of turns. The quality of B1, so the amplitude of B1 is dependent on the number of turns, but they do not necessarily follow the relationship which you would like. The consequence is, if you add more turns to get better B1 amplitude, you get more and more inductance, and more inductance pushes you further and further from the reactance which you want to satisfy that equation. You get bigger and bigger capacitors to correct for it, and the bigger your capacitor is, the more reactance that presents, and therefore the more resistance you have to the flow of the current. The ideal coil for tuning and matching probably has zero inductance. The ideal coil from a perspective of B1 has infinite inductance. So you are constantly fighting between the two to find a happy medium. If you are at a high frequency, you have the luxury of picking those things. In order to get down to the frequencies that we make probes at, 5-10 megahertz, you need to have quite a high inductance to actually be able to get a low resonance condition. So the only things you can change are the inductance and capacitance to pick the resonant frequency. And basically you end up having to have a big inductance to push you physically down in frequency. You can calculate it, but it's much easier, given that it's just a bit of wire, to wind it and look at what it resonates at, and then tweak the number of turns until you find one that works. The counter argument is, if you are a really long way off, a little calculation can put you much more into the right ballpark to start with.
We build the magnet with the software. Is something software?
It's just not very good.
Not that we put the capacitance and then use it.
Yeah, so you can, there's not much software for it because the tuning and matching bit is quite straightforward to plug the numbers in. You can simulate the field in the solenoid. But again, any solenoid will always be better than anything else. And actually, the best solenoid is coil separated by its radius of wire. So you have 2R, 1R, 2R, 1R, 2R, 1R of wire and gap. And so actually the benefits of simulating it for that are pretty much non-existent. When you would want to simulate it is in the slightly more unusual geometries. So if you are doing like the Bruce Balcombe trick of sticking the edges up at the coil to try and capture a bit more field, that's best simulated because that's a bit difficult to get right. If you are trying to do it so that you're making a coil shaped to a given geometry, because the field lines are strange, that's worth simulating. But for the most part, our approach is start with 10 turns, stick it on the analyzer and see what it says, and then do twice that many if it's far off and go backwards and forwards. It's not a good approach, but it is definitely the quickest. Okay, so we need to have a system which can measure what that resonance is, and we need to do that to look at a range of frequencies. So we are interested in how much energy is reflected back. So we are now measuring the volume of the puddle on the floor of the first pipe. If you are off resonance, the puddle will be infinitely large because it's the equivalent of having no pipe. As you approach resonance, you will get more and more and more and more water into your bucket, and therefore a smaller and smaller puddle. When you are on resonance, you will have 100% transfer, and therefore you should have nothing at the point at which you're on resonance. Next slide, please. So this is the thing that does that job. This is a network analyzer. The network analyzer on there is everyone's favorite. I actually like the version before that, but they are about £30,000. If you are good on eBay, you can pick them up for about £5,000, but they are always thousands of pounds because we like them, and we really like the one that was before this one, and so that one's still like 7,000, even though it was only 10 when it was new. So this is not particularly affordable unless you happen to have them kicking around. The next slide is a slightly better option. In that these are more like £50 to £100. The one which you'll use tomorrow are about £500, which plug into the computers. These are literally £50 if you don't mind waiting for them to ship from China, or £150 if you want to buy them already shipped. Obviously, I think the £30,000 one is much better, but this will do as good a job in telling us where our resonance is. And for something which you probably won't do that often, it's not necessarily worth having the really, really expensive version. Okay, so on the next slide, we should have the output that you get from the network analyzer. Have you tuned and matched stuff before? Let's have a show of hands if you have tuned and matched things before. You've tuned and matched things before. Stick your hand in the air. Thank you. Okay, so that's not many hands. So this is the output of the network analyzer. The x-axis on the network analyzer is frequency. The y-axis is the amount of power which is reflected back to the network analyzer. Off resonance, everything is reflected back. So we have a very high number. As you approach resonance, it gets less and less and less and less and less until you're on resonance and you have nothing reflected, and then it goes back up again the other side. If your goal is to tune your probe to the red line, the left one is what you are trying to achieve. If the frequency is wrong, it looks like this, and we still have nothing reflected here, but it is in the wrong place. So this is well matched, but poorly tuned. This one is tuned right, it's bang on the right frequency, but you are still getting some reflection of power. Probably until yesterday, I think we still believe what we were told, which is this is what you are trying to achieve on the left. I think I am now convinced that actually this is just fine. If you have this really, really deep peak, you have no choice but to be exactly here. If you have this peak, you can afford to be here or afford to be here, and it will still work absolutely fine. So actually this is not necessarily anymore not the target. If we can have the next. Yes, so it still needs to have a dip, but it doesn't need to be an extremely deep dip. Okay, this may or may not be news to you, I don't know, but we're going to cover it in case. The y-axis on almost every network analyzer is not linear. Okay, the y-axis is a logarithmic scale, and the y-axis is measured in decibels. And decibels is just a reasonably well agreed upon logarithmic scale. It's really not straightforwardly obvious how it works, but once you know how it works, it's very easy to apply it. The problem is there are two scales, and it depends on whether or not you are talking about voltage or you are talking about power. If you are talking about voltage, every time you change the decibels by 6 decibels, you halve or double. So if it becomes minus or smaller, you halve it. If it becomes positive or bigger, you double it. Power does the same thing, but it's every 3 decibels. The problem is if you don't know which one it is, so for example, the Kia spectrometer uses decibels as the amplifier power, and that is measured in power rather than voltage. Therefore, you are looking at 3 decibel differences to halve and double things. The reason I am telling you this is because the y-axis, if we go to the next slide, of the network, and I lied. There is a further unit, which is dBm, which is decibels relative to a milliwatt, where 0 decibels is 1 milliwatt, 3 decibels is 2 milliwatt, 6 decibels is 4 milliwatt, or -3 is half, -6 is a quarter. Okay. Now the next slide, please. So this is this decibel axis. And the reason it's important that we know it's a decibel scale is it looks like this peak here is quite a big dip, but actually it is a mammoth dip because this has halved and halved and halved and halved and halved and halved again. Okay, so actually that is a very, very, very deep peak. The reason that we use decibels is because they allow us to focus very easily on orders of magnitude of change on one display. If you display this linearly, you end up going along and then all of a sudden it just drops off the screen and then it comes back on and it is kind of useless. So it's important that we know that this is a log scale. If we can look at the next slide, we will see more like the trace of the good old Agilent analyzer that we all love. And we will see now there are 2 plots. This is for an NMR coil, 60 something, I think, or is it 6? It's 6. The top plot is the plot which we have just seen, and we can see that this is beautifully tuned and matched perfectly on resonance at 6.284 megahertz. The bottom plot you will occasionally see in books, and this one is the one that's useful for science. So this is actually a measure of our impedance on here. And if your marker is bang on this line at 50, everything is perfectly matched and tuned to your resonant frequency. They are nice if you are sciencing. The top one is much more easy to use and to see what's going on. Okay, we are nearly there. Next slide, please. We have one more thing to look at with regard to these peaks, which is something called Q, which stands for quality. And this tells us how deep those peaks are. And this was the There's more like an acceptance this week that we are quite happy to have poor Q. So Q tells you about how deep your peak is relative to how wide your peak is. If you have a very, very wide peak that is very, very shallow, it has a low Q. If you have a very narrow peak that is very, very deep, you have a high Q. If you have a high quality factor, it takes a little while for your coil to settle back down after you have sent an RF pulse. And it means you can't measure very, very short echo time things. And it means you have to be extremely on resonance all of the time, or you very quickly wander out of tuning. If you have a bit of a rubbish Q, you have a nice range that you can explore without having to retune stuff. And it doesn't actually, in the grand scheme of things, make that much difference to what's really happening. An important thing to remember again is this is a decibel scale. So the difference between the first 3 decibels is a half, but the next 3 decibels is then you're into quarters and eighths and sixteenths. So it starts to get less significant towards the bottom. The Q factor has resistance in. This comes back to the question about how many turns you have and the gauges of wire. If you can minimize that, you give yourself a much better coil. Next slide, please. Okay, is everyone happy with tuning and matching? Is anyone unhappy with tuning and matching? Would you like to talk about tuning and matching? It is. What I would say, so we would normally put variable capacitors on the 2 capacitors and you twist them and their value changes and you can move the peak left and right and up and down. It is a process which is difficult. It is a process which you'll all get to experience tomorrow. But it's something that you have to do. These are the boards which you will use tomorrow. There's some capacitors on and a plug for the inductor to go on and some things that you twiddle, which are the capacitors. That really is all there is to it. But you will see tomorrow that it is really difficult. Leonid grilled someone, I can't remember which of you it was, about having static capacitors instead of having variables. I think it was Erdem. And this is one without variable capacitors on, but you need to know what you want to make the board with the static capacitors on. So it's good down the line, but these are much better if you're still developing what you're doing. Okay, the last thing that we need to look at today is shielding. And for shielding, there is another effect which you have to appreciate to understand how shielding works. And it is another treat of alternating current, which is called skin depth. If you have a wire and DC is flowing through it, it uses the whole of the wire. If you try and switch the current backwards and forwards in your wire, every time the electrons move this way, they create a magnetic field and it repels the electrons and it makes it harder to change the direction. Your charges in your wire respond to that by fleeing to the outside edges so that they cannot be pushed around by the field that's there. And it means that the higher the frequency is, the less of the wire is used to carry current. So that is the definition of skin depth. Is the amount of thickness in the edge of the wire that gives you a drop in amplitude of the voltage going through it of 1/E. That's the point at which it's 37%. I tell you this because this is how shielding works. I'm not going through the equations on the top because can you click the link and see if it works? But are we sharing a PowerPoint rather than the screen?
I'm just. Yeah.
Nice, because you can stick numbers in and it will give you the answer. So we do not need to do the equations. If you put in the frequency that we've got, so let's have a look at 5 megahertz, and then we'll do it for copper in the material. And then if you click calculate, it should give us the skin depth, which is 29 microns. So if you have a bit of wire and you put alternating current through it at 5 megahertz, it will only use the outer 29 microns of the wire, which is a very, very small amount. The reason this is useful to us is skin depth applies regardless of whether or not you are flowing current through the wire or whether or not you are trying to block RF from other places. 29 microns is not a lot. I think if we go back to the PowerPoint, I will save embarrassing myself by forgetting how thick the copper is on the boxes. I thought it was, but I think that's just what we tell the milling machine.
Slightly less.
Yeah. So this is the material that printed circuit boards are made from. It is 2 layers of copper on a bit of fiberglass resin, fiberglass in resin. And then on the next slide, yes, very good. So these are typical skin depths, about 30 microns for 5 megahertz, 65 for 1 megahertz, and 20 for 10 megahertz. So they're always quite small numbers. That will reduce the amount of noise getting into your box at 5 megahertz by 37%. If you do it again, you will go to the next bit of the exponential. If you want to block it entirely, you need 5 lots of that, or 7, but 5 is good enough. 5 is 99%. This is the 1 ounce a square foot, which is 35 microns. And there is a bit either side of it. So we will do 2 lots of 37% of reduction just by sticking the probe in a copper box like this. It is why a bit of very thin copper foil on the probes, which we saw yesterday, is enough to get rid of a load of noise. Okay, so you do not need a lot to make an enormous difference to your signal. If your signal to noise ratio is good, doesn't matter. So the commercial instruments that you've got down in the lab, they're fine. Hello.
So do you need it?
No, we're nearly done for the day. It's very good, thank you. Commercial instruments that you've got in the lab probably have SNR in the thousands. The instruments you will build tomorrow probably have SNR in the ones. If you have a signal of 1 and a noise of 1, you don't see anything. So this becomes your friend. If you ditch 37%, you can start to see some signal. If you ditch 2 lots of 37% by having 2 layers, you can actually see signal. Almost nothing that we build, I can't believe we will build anything tomorrow that will work without the box. We will try it. It depends a bit on how noisy it is. Our lab often needs a box and a box and a box and a box. It depends on what else is going on in there, but the shielding, it's enough just to have a bit of copper foil wrapped around it. We tend to do that right on the outside and the whole thing will go into the box. You can, yes, but it must be continuous. If you have breaks in it, it will no longer work. Thank you. We tend to do it around the outside, but you can do it on the inside of the magnet and just have it around the outside of the RF coil. It depends on how much space you've got spare, but it makes no difference. Okie dokie, next one, please. We're done. This one was a bit more physicsy, sorry, but hopefully you appreciate at least the need to do some tuning and matching. You will get some experience tomorrow on how to do it. There is nothing which can possibly replace just doing it. The first time you do it, it will take hours. On the old MRI scanner, you could do it whilst you're having a conversation and drinking a coffee, not in the lab. But it's dead easy. It just takes a lot of time to get to grips with the fact that both of them change everything. But hopefully it's at least a bit of a touch. So, sorry, go on. Yes, please.
The thing is, it's very interesting, and most of the stuff that we have discussed today is physics. I'm basically a biologist.
Yeah.
So for me, and I'm looking at the interface of chemistry and biology. For me, the important thing is how to prepare this sample and how to analyze the sample.
Yeah.
So these things are important for us.
They are. That's why we talk to biologists and chemists. Yeah. They tell us how to do that bit.
Resolve the structure of compounds. For example, Okay, almost 16 years ago, I spent some time in Cape Town, South Africa.
Okay.
And over there, I was working on fungal solubilization of low rank coal, and chemical commodities were coming out after the depolymerization. And at that time, I was collaborating with the chemistry department, and I learned the NMR, how we can solve the structures.
Yeah.
So yes, these kind of exercises are very, very important for us, for me actually.
So we were having a conversation earlier, which I think is useful to have now. The width of the peaks in the spectra are directly proportional to the homogeneity of the magnet.
Okay.
Okay. So if we have a beautiful spectra with infinitely narrow delta Diracs everywhere, and you can perfectly resolve all of these crazy chemical structures, the homogeneity of that is about it's zero. The variation of the field over there is zero.
Yeah.
As you decrease the homogeneity of the field, you increase the width of the peaks, and it's the integrals that are always constant. So as the as the width goes wider, the height goes down. As you decrease the homogeneity further, you start to lose the peaks, and they all start to kind of merge into one. The homogeneity of these gives you a spectrum that looks like this.
Yeah.
The clever thing is to ditch that information and get it from somewhere else. So we can never, the magnets that I've shown you today can do this. So you can do spectroscopy fine in a really good Halbach cylinder, but it needs to be a really good Halbach cylinder. So the one which we've got, which we purchased commercially, took 6 months to construct. And the magnets are separated by pages of phone book, and the positioning of the magnet is controlled by slipping out phone book pages. That is the level of precision that you need to get a spectrum, and the spectrum on that looks like this, not like this. The only way to get good, really good spectra is to have a beautifully homogeneous magnet. And you get desktop ones, and they're baked and they're expensive.
For example, if you are trying to solve the structure of the compounds, for example, aromatic compounds, aliphatic compounds, I think it will be much easier compared to solving the structure of the proteins. What do you think?
I can tell you much more about a protein than an aromatic because I don't have access to this.
Okay.
But I do have access.
So proteins are more challenging? What do you
No,
think?
proteins are much easier.
Easier?
Because the shape of the you can't, it's impossible to resolve anything without spectroscopy.
Okay.
But what I can tell you roughly is the size of the protein and the aspect ratio of the protein.
Okay.
By looking at how it tumbles. So the way that it moves will change its relaxation. And from that, you can get some interesting information. Yes,
T1,
so that's in T1 and T2.
This is in T1, T2, but how about the complete structure of the protein through NMR? Like
yes, but you're into spectroscopy. You're into high field magnets. You're into hundreds of thousands, if not millions.
It's more complicated.
It's actually dead easy. So if you give me, I mean, you can. If you give me £200,000 now, I will buy a boat. By tomorrow, I will. That's probably pushing it. By next week, we could build you a supercon magnet that will do spectroscopy. But it will always cost that amount of money because the materials needed to make them is hard. They're cryo vessels, supercon magnets, and it's really difficult. What we like is to not try that and to get the stuff that's useful and interesting without it. So T1 and T2 can tell, and diffusion.
I think we need to introduce these kind of techniques
things
in my institute. Okay, NMR, there are few NMRs Like if you have you heard about Hussain Ibrahim Jamal Research Institute? They have many NMRs, several NMRs, but these are the state-of-the-art equipments.
Yeah.
Nobody is working in terms of T1, T2 relaxation in Pakistan.
Nope.
So I think we'll spend 1 month in your lab if you spend over there. So that would be a very good
thing to take.
yes.
Yeah. So it's our second session now, because it should have been electronics now. So first session tomorrow is electronics, but the second session is getting stuff from these for T1, T2 diffusion. And so hopefully by the end of that, you'll have at least a bit of a...
is much easier compared to the spectrophotometric analysis that we do for the
It's
solution of-
different. It's different. So I can give, so let's say we get an undergrad for a fortnight. I can get them set up to resolve spectra. If I get the same undergrad for a fortnight, they will have just started to get to the point where they can grasp how to analyze to get really neat stuff out of T1 and T2, because this is really well defined. And as we heard in a lot of the talks on the first day, we are still doing I'm not sure whether or not it's this model or this model. Should it be mono exponential? Should it be bi-exponential? What is this component? What is that component? Because it's not well defined, but I can upload this onto some fingerprinting software and it will say that's an aromatic, this is an aliphatic acid, this is a
not the complete structure.
not the complete structure, but if you give me a sample
okay
and £100,000, we can stick it in the NMR and then we can do big XRD, what's this called, synchrotron,
So
I will give you the structure.
And how much it costs to develop this T1, T2 based NMR?
So the whole thing,
Yes.
not very good, but the whole thing is about £1,500 with
It's
everything.
not expensive.
Yeah.
Okay, we'll think about it.
Don't know. Any other questions? There was something I was going to conclude. So tomorrow we will start with electronics, not much physics. At nine, Siobhan's saying 9, it's not me. At 9, we'll start with electronics. Then we will do pulse sequences, or how to view CPMG, and then 5 or 6 slides on how to set parameters, and then we'll build stuff. But we'll do the same again. We'll just leave it fluid and we'll stop for coffee at coffee time. Okay. That's it. Thank you.
Yeah.